Yeah.
Okay. All right, cool. Okay. Yeah, so the second goal is to examine the strengths, weaknesses, and underlying assumptions of proposed methods and establish best practices in evaluation of these methods. And the third goal is to discuss the various nuances of explainability and brainstorm ways to build explainable CV systems that benefit all involved stakeholders. So here's the workshop schedule. Also, everything is on our website. It's very up to date, so you can always check it out there. All events will take place in this room, except for the 2 poster sessions and the lunch social, which are highlighted in gray. And we'll kick off the workshop with 2 fantastic invited talks, and then have a spotlight session with 3 spotlight talks, and then move to the West Exhibition Hall, which is the floor below us, specifically to poster boards 203 to 241 for an in-person only poster session, and then head off to lunch together in the West Ballrooms if you're interested. After lunch, we'll hear 2 more invited talks and then 3 spotlight talks in the second spotlight session, and then head again to the West Exhibit Hall for the second poster session. And we'll wrap up the workshop with 2 invited talks and a closing remarks session where you can ask us questions and also give us feedback about what worked well, what can be improved in the future, and so on. So we're really excited about our invited speaker lineup. This year, we really try to invite speakers who can share different perspectives on explainable AI, ranging from computer vision and machine learning to human-computer interaction, visualization, and even AI ethics. All talks will be 25 minutes long and will be followed by a 5-minute live Q&A session. So please think of questions as you listen to the talks. And moving on to, some statistics. So this year we call for papers and demos in 2 tracks. The proceedings track received max 4-page submissions of original work, whereas the non-proceedings track received max 2-page submissions or extended abstracts of published, accepted, or ongoing work. And all submissions went through a review process, and accepted work in the proceedings track were published in the CVPR workshop proceedings. So here's a quick overview of the 17 papers that were accepted to the proceedings track. If you go into our website again, you can see all the PDFs and even video recordings for some of them. And here are the 5 extended abstracts that were accepted to the non-proceedings track. And I just really want to emphasize that all of this would not have been possible with our wonderful program committee. We'd like to express our sincere gratitude to everyone here who responded to, our last minute emergency review requests, or just, were super responsible and gave us all the reviews by the time. And yeah, it just would not have been possible. So yeah, I just wanted to acknowledge them publicly. Moving on to logistics. So I guess I covered that the invited talks will be 25 minutes, followed by a 5-minute Q&A. Our spotlight talks will be 8 minutes, followed by 2-minute Q&A. And if you want to ask questions, feel free to type them into Zoom and Rocket Chat. We'll be always monitoring them. Or you can also raise your hand. Then we'll either pass the mic to us, or I guess you can also come up to this mic stand and ask the question directly. For the poster sessions, they're unfortunately in person only and will take place in the West Exhibition Hall, again, boards 203 to 241. The workshop organizers told us to tell all of you that all posters must go up at the poster session, not prior, and then taken down at the end of the session. But for authors who couldn't attend in person, we will be playing 2-minute video presentations on loop throughout the poster session in this room. So you can always also just stay in the room and check some of those out, but also, spend some of the time engaging with the actual authors at the poster session. So you can, do back and forth for both poster sessions that are happening. In our workshop today, we expect everyone to engage in respectful communication. We hope to foster an inclusive and respectful conversation between different, potentially conflicting perspectives. So please do not do the following, insult, bully, disparage, shame, or mock others, campaign, fundraise, or lobby for active political candidates or pending legislation, discuss or pressure others to change their religious beliefs, or share inaccurate or misleading information that could cause fear, disruption, or harm to others. And last but not least, we really hope you have fun and also tag us on Twitter. We would like to know what events you enjoy and would really love to amplify your work as well as much as we can. So please do that. And with that, I will pass it on to Deepti, who will introduce our first invited speaker.
Here. Hello, I'm online here.
Oh, okay, that's great.
Actually can't start my video because the host has stopped it. It's telling me. So maybe you can allow this.
Vikram is there.
Okay. I think you just need like stop share. So once it goes.
Oh, okay. Marina, I'll quickly introduce you and I'll stop sharing and maybe then you can unmute your video. Shall we try?
Sure. Thank you.
Okay. Hi, everyone. Welcome. We're very excited to have our first speaker, Marina, and she's here to talk about talk on how much can I trust you towards understanding neural networks. Marina is the head of data science and bioeconomy department at the Lebanese Institute for Agricultural Engineering and Bioeconomy, and in joint appointment as professor for digital bioeconomy at the University of Potsdam. Her research focuses on explainable AI and the development of methods that enable a holistic understanding of AI models and their decisions. Dr. Hanne received her master's and PhD from TU Berlin. With that, Marina, take it away. I am stopping my screen share.
All right. It's still not possible to start the video, but I can share my screen. So, can you see my screen?
Not yet. Give us 1 minute.
Yeah, no.
Oh.
Okay.
Can you see it or not?
Yes, on Zoom, yes.
Okay, but unfortunately, I can really not start my video. So it's telling me that the host need to, that the host stopped it. I mean, it's also okay if you cannot see me. It's already picture, but
Sorry, give us 1 minute. We still have time, so let us sort this out.
Okay, sure,
and
sure.
get started.
Should I stop screen sharing again first?
No, your screen is fine. We're just trying to show your slides and also allow your video.
So you can see that. Right?
Yeah, we can see your slides. We're just trying to.
Yeah.
Finally. Sorry, everyone. Give us a minute. We see, Marina, as a quick update, we see your slides. We're just trying to get your video on the screen
Okay,
for the in-person attendees.
Might I suggest that maybe if you make her as a co-host, then she could share her video as well? Sometimes this happens also when we do like online exams. So if you're
Yes,
a co-host, yeah.
we're trying that right now.
Ask her to start now.
Can you try starting your video?
Well,
Mhm.
I think it worked.
Oh, amazing. Okay, we're just gonna make it a little bigger and then
Mhm.
is that better in-person attendees or would you prefer the side view? That's good. Okay. All right. Marina, do you want to take it away?
Yes. Okay. Thanks so much. Yeah, also for the introduction. So my talk today is about how much can I trust you towards understanding neural network. And I'm super excited to be today, yeah, the first keynote speaker in this great workshop. So yeah, I mean, you already introduced me. So since last year, I'm professor at University of Potsdam, and I'm also leading the data science department at the Leibniz Institution. And yeah, what is else important, except that I'm a mother of a 5-year-old, which is sometimes also quite challenging. I'm the head of UmiLab. So the research you will see in my presentation today is yeah, from my colleagues. And our research group is called Understandable Machine Intelligence Lab, short UmiLab. And this picture, yeah, came up because we started, so I started my junior research group at TU Berlin 3 years ago during Corona time. So this is why it's just us holding UmiLab into the camera. Yes, and so actually I would like to start, because it's also the first talk today, with a brief overview. So why do we need explainable AI? And yeah, I brought this small introduction motivation example, and I would say, like, in the Sci community, this is one of the most famous forces since some years, because, like, when we take a trained model, which can classify between like a lot of different classes, horses, owls, cars, people, whatever, like a lot of different classes, this model correctly classify this image to the class horse. Well, great. Now let's take a different image. So this image, for instance, of the owl class, and the model, unfortunately, again, say it belongs to the class horse. So we wonder why, but this, yeah, the model does not really tell us why it's made this wrong prediction in this case, because it's behaving like a black box, right? And here is where explainable AI comes into play. So exactly, local explanation. So what we are doing is we can take the prediction of the class horse, feed it back through the model by some explanation methods, rules, and then we might get this kind of explanation as a heat map, where we see the most important pixel areas highlighted in red that the model used in order to make this prediction to the class horse, right? And what you can see here is actually that not the owl was responsible for the prediction, but it was this text in the lower left corner. And the reason behind this is that during the training phase, the model has seen a lot of horse images with text in the lower left corner. And this again is because the photographer of a lot of horse images has put the name and the web address in the corner. And this, of course, the model used then in order to classify, yeah, horse images or whatever images with a text to the class horse. So this is what we call the clever Hans artifact. Artifact because there was a correlation with this text, what we also call sometimes watermark, when this text is on a, or some symbols are on an image. And the model learned this because there were some correlation in the training data set with the artifact and the object of interest, right? So why are we calling this now clever Hans? Because there was actually a horse in the 20th century with the name Hans. And it was claimed that this horse can do arithmetic and some intellectual tasks. but at the end it was found out that the horse had no intellectual ability at all. It was just directly responding to kind of the cues in the body language of the owner. And this is why now people are referring to this artifact as Clevant's artifacts. All right. So yeah, what else? Why do we need explainable AI? I imagine we have trained such a neural network to distinguish between cat and dogs. And then the model gets those images and says, okay, this is all dogs, right? Obviously, it's not. So there's a need to understand on which input features the model is based the decision, right? Okay, so in the last, let's say 10 or maybe even 12 years, there have been so many different methods in explainable AI field developed. And since also I'm the first presentation today, I thought it would be great to give you first brief overview of the different types of XAI methods. So let's start with the model-aware methods. What does that mean? So model-aware means we have access to all the model parameters and the architecture. We just have kind of white box access, right? It's not a black box for us. And what can we do there is like a method called LRP, layer-wise relevance propagation, developed by some of my colleagues. They take the output prediction, so this image of a cat is correctly predicted to the class cat, and then this prediction score is back propagated through the network by some rules and then distributed over the input image in such a way that the final prediction score, so f of x, right, is finally, like by some rules where we multiply the activation of the forward pass by the learned weights, by the relevance, and in the first place, the prediction score is then distributed over the layers to the input image such that the sum of the relevances of all pixels is equal to the prediction score. And so we then understand which regions, which input pixels were responsible for the prediction of the model. Okay, so then there's a different category of XAI methods, the model agnostic methods. And here we have given our black box, so the trained model, but we don't have this white box access. So we have no clue what is the model architecture, what are the learned weights. So what can we do? We can just change our input image and observe how the output, how the prediction score is changing, right? So this image is correctly classified to the class dog. And with a prediction score, let's say, of 0.99. Now, what can we do? We can black out, for instance, some of the pixels of the input image. And what we see here is from 0.99 from the original prediction score, we get a small decrease. But now, like kind of removing input pixel information from part of the dog, we get an even more reduced score here. And so we can go over all the different regions of our input image and report the decrease in the prediction score here. And so we get an intuition about which input region the model is using in order to make the prediction. So now we have the model-aware methods and the model-agnostic methods. A third category is the self-explaining models. So what's that? Well, so this year is just a normal convolutional network, right? Where the final, so we have convolution layers, convolution poolings, and finally we have some kind of fully connected layer where the decision is based on this latent representation where we have no clue what the model has learned here, right? So we don't understand the final decision. And in case of self-explaining models, for instance, for the Prototypical, which was published first in a paper, this looks like that, deep learning for interpretable image recognition. So what they did is they include a new type of layer called the prototypical layer. And in that layer are different prototypes from the training data learned for each class. And so that the final decision in the fully connected layer is based on some similarity score from this test image, right? We want to classify this image. We take some patches out of this test image and compare this to our learned prototypes, which we humans can understand. And then we can just comprehend where the decision is based on. Okay, so there could be another category, which I sometimes call combining models. So you could also combine model-aware methods with self-explaining models, or I will show you on another slide that you can compare global explanation methods with local explanation methods. But first, let's have a look at the global explanation methods. So first, what is the difference? In a case of local explanation, we are interested in understanding the prediction of a model for a specific data sample. So for instance, for this specific image, we are interested why the model classifies this to the class Causal. And in global, we are going away from single data points and are more interested in the concept the model has learned, for instance, for the class Causal. So let's consider this trained neural network here, which distinguishes between 4 classes, dog, cat, boat, bird. And this image of boats is correctly classified to the class boat here. But now we would like to know, how does the model kind of see the class boat? So what of a concept the model has learned in that neuron, for instance? But we can do this for all of the different neurons in the whole network. So what we can do is, and this is a method called activation maximization. So meaning we want to maximize the activation of this neuron now. So we are leaving the whole network fixed, but we are optimizing now over the input image, such that finally so out of our optimization problem, there comes an image that is maximally activating this neuron here. And what we can see there is then kind of the concept the model has learned, right, for the neuron. And what we can see here, observe, is like the concept of a boat on water with maybe some mountains in the background or city. So the model really understands the concept of a boat. Okay, so what can we do with this? For instance, now taking an image of 2 cows, and we double the image, so we copied it and placed the Clever Hans artifact, the watermarks, the text in the lower left corner. And we were interested in like feeding each image separately to the trained model, which neuron of each layer are both images maximally activating, right? So and what we can see is in the very first layer, so here are the neurons of the earliest layer, and here are the neurons of the later layers, is that in the first layers, both images are activating the same neuron the most, right? So these are the layers where the most basic concepts have been learned. And in the later layers, where a more complex concept has been learned, we can see that the cows with the text are really kind of maximizing the activation of a neuron that learns some textual patterns, which is not used this neuron from this image. Okay, now combining local and global explanations. So we computed this activation maximization image. So it's global explanation for the class horse. I sometimes also call them magic mushroom images because they somehow really look fancy. And now we were interested in like, is the model using the horse or the text for deciding for the class horse? So we feed now this global explanation back into the model and use different, local explanation methods, 3. And if we have a look at the GradCam, it's the most obvious here. You really see that the model is using the text patterns instead of the horse. All right, so that was a brief overview of the kind of different categories of explainable AI. And now I would like to take this example, this image as a running example. So this image is correctly classified as class Causal. And now we are interested why, right? And we computed now the standard LRP explanation. And what we can clearly see is the model is using the information of the Causal here to predict this image to the class Causal. But we also can see that the model is using a bit of the lamppost, right? And also, it's hard to see, but maybe you can there, also the cars and the street are a bit of important for the model to predict this class. Well, and then we thought, can we maybe do better here? So can we maybe extract what are the most relevant features for the model? And what we did there is we used information from Bayesian neural networks. So small recap, what are Bayesian neural networks? So this is not a Bayesian neural network, but this is. What is the difference? In a Bayesian neural network, we learn between 2 neurons, 1 weight, right? So in a normal neural network. And in the Bayesian one, we learn a whole distribution for each weight connection between neurons. So how can we use this then for prediction? Again, here's a normal neural network, right? We have just, so there for visualization, just 1 digit between the 2 neurons. And here we have a distribution. So what can we do? We can sample from a distribution, right? So we sample once, and we can then feed in our input and get an output, right? And we can sample again, and we will get a different output, a different prediction. So we can sample because we learned the posterior distribution over the weights based on our training data. Okay, how can we use this now? So why are we doing this? Okay, consider now this input image of a cat. So we feed this into our Bayesian neural network. Of course, first we have to sample a lot of times from our Bayesian neural network, so n times. I like to call it subnetworks, right? Each having different weights. And in each of the subnetworks, we can feed our image of a cat in, and we get for each subnetwork a prediction. And then we can take, for instance, the mean prediction, we can compute the variance of the prediction. So we are getting some kind of uncertainty information, and not just as a normal neural network, 1 prediction, we get just more information. And then we were thinking, how can we take this uncertainty information and transfer this into the explanation itself? Well, so each prediction we can feed back into the subnetwork towards the input image and get an explanation, right? So we get n different explanations, and we can again compute the mean explanation, for instance, but we can also compute the union and intersection. So the intersection, for instance, what does that mean? That means we are interested in the features that all subnetworks agree on, that those features were important for the submodel, right? Subnetwork to predict this image to the class cat. And these are then the most certain features you can think about. And the union, there you are more interested, like, okay, where about all the features which might have information about your class. And then you can, for instance, cluster your explanations. Okay, so back to our running example. We now sampled here 5 times the subnetworks from our Bayesian neural network, and we get 5 different explanations. Of course, we did this 100 or 1,000 times. And then we computed the intersection explanation. And what we see here is indeed only the Causal got relevances. So we can now clearly say, okay, the model is using the Causal preferred instead of the lamp post or the cars over here, right? And then we thought maybe we can even include all this kind of uncertainty information in one explanation. And this is what we called UAI plus, so union and intersection plus explanation, where you see the percentile information. So recap percentile of 0 and between 0 and 20 mean the opposite, like at least 80% of the networks agree that a pixel was relevant for the model to predict that specific class cat here. So you see the eyes were the most important features and the nose, and here are the less important features. Yeah, and we also test our method on different data sets. For instance, for the histopathological experiment, we could directly point the expert to the most important areas where the model thinks so there are cancerous cells. Okay, and back to our Clever Hans experiment. So what does it mean? That indeed it is a Clever Hans image because the text is the most important feature. And also the tree over here is kind of an artifact. So, okay, so let's make a different jump to another method, which we published recently and which is now accepted at TMLR. So it's called Dora, and it's a data agnostic representation analysis. And for this method, we were interested in trying to understand the network from, like, as it is written here, from a network perspective. And the interesting thing is we try to do this without using any data set. So you give me a trained network and I tell you exactly this thing here. Where are the outliers in your network, kind of the neuron that might have learned Clever Hans artifacts? So maybe first the reason why we try to do this in a data agnostic fashion, meaning without a given data set. So let's think about the CLIP-ResNet network. So maybe a lot of you will know what is the CLIP model. This was uploaded in the internet by OpenAI. So OpenAI is a company who published also ChatGPT. And so no one knows what this CLIP model was trained on, right? No one has an idea. But people are using the CLIP model also in safety critical applications. So we kind of should be aware, like, what is inside of the model? Are there some artifacts maybe? And what we did, now first, in order to show you why we sometimes need global explanations and we should go away from just having single data sets, we picked one neuron, so unit 744 in this huge CLIPNet model. And we took then the ImageNet data set in order to try to understand what this neuron has learned for a concept, right? So we feed all the images from ImageNet into this model and observe the activation of this neuron, right? And of course, the images which maximally activate this neuron kind of has a concept in it which had been learned by this neuron. So and this were the most activating images. Maybe one of you recognizes the concept, so but maybe it's also not possible. So let's jump to the global explanation. Maybe some of you now will recognize it, but I guess you have to know the movie. So actually, this neuron is a Star Wars neuron. It has learned the concept of this lightsabers, right? And this should, kind of motivate why mostly it is not enough to use just one data set in order to understand your network. All right. So how is now Dora working? So first of all, so this is now our trained network, right? Where we pick one layer. So this could be any layer, but mostly it makes sense to take the last convolutional layer in order to have the neurons which has learned the most complex concepts, which we humans might also understand. And for each of this neuron, we are now making a global explanation. Remember back this boat image where we saw the boat concept. So for each neuron in this last convolutional layer, we are now generating a global explanation and image, which are those here, S1 to S5. So we are generating the synthetic activation maximization images. So second step, we are taking all our generated global explanations and feed them back into our model, right? So that for each image, we get now the activation here of our neurons where we created the images for. Okay, so each global explanations give us one activation vector here. Meaning we now have a matrix of 5 times 5 values. And what can we do there is we can do, for instance, an outlier detection method, right? Trying to find neurons that are activated like most differently to all other neurons. And when doing that, what we find in a totally automatic way is that this ResNet 18, which people highly use, also again for safety critical applications, that neuron 145 is considered to be the highest outlier by Dora. And what you can see here actually is that this neuron has somehow learned the concept of symbols. And what we figured out is exactly that those symbols are shiny symbols. And also in the neighborhood of these neurons, there are kind of those symbols learned by the neurons. And this is since there are multiple images, you know, with this with Chinese symbols on it in the internet. And there are also, of course, images which have Latin text on it. So we also found as an outlier this neuron which has learned the Latin text. And what we further showed, and here comes kind of the risk, so why this is important. Imagine you download this ResNet 18. You are now having your chest X-ray images, so grayscale images, medical data set, and you're going to fine-tune your model. And what happens is like that for the fine-tuned model, even on grayscale images, this clever Hans survived. And with this knowledge, which you could generate in an automatical way, without any data set, so with this knowledge, you could, of course, go now ahead and, you know, insert somewhere either a shiny symbol or a Latin text or some other symbol, which is similar, and you could manipulate the prediction. And this is something you don't want to have in your network, right? So this kind of possible risk, or at least you should be aware of this. Okay, furthermore, back to the CLIP model, where no one knows what it was trained on. What we found by applying Dora, so each dot here is one of the, I don't know how many representations, but each is one neuron in the last convolutional layer. And what we found as an outlier is, for instance, neuron 95, so which learns some pornographical stuff. So the network really has seen that kind of images and content. And also as an outlier was the neuron 946, so which learned drugs. So it's kind of Mariana leaves, you can see. And also as an outlier, like the neuron 135, which is kind of a World War II neuron. So it is pretty interesting that, you know, no one knows where the model is trained on. Now you can kind of figure out in an automatic fashion what is inside of the model, what has the model learned. Okay, so last jump now actually. Back to, maybe now some kind of also issues with explainable AI, which I worked on in the last, let's say, 2 years. So there's so many different explanations out there, right? And the question is, given some real-world problem, you get a prediction, you want to know what's the predictions based on, you choose an explanation method, but which one should you choose? And how you can be sure that your explanation is correct, right? That it's faithful. So we have now our model. The model is making a prediction. So we want to explain the prediction. We compute several different, like integrated gradient, saliency maps, different explanation methods. And what people came up in the recent years is they are evaluating the explanation now by different criteria in order to guarantee that the explanation method is working correctly.
And we just wanted to let you know we're almost at time. So if you can wrap up in the next
one more minute, okay? Okay, perfect. And one of my PhD students, Anna, came up with a toolbox where she implemented all the different quality metrics like faithfulness, robustness, complexity, and so on to measure the goodness of an explanation method. And what we now recently done is we kind of brought the evaluating problem to a meta-evaluation problem because, and this is kind of my two last sentence, who can really, like, who knows how good an evaluating metric is working, right? Because you don't have you don't have a ground truth for your explaining model, and you don't have a ground truth for your evaluation metric. And this is why you should also focus on to evaluate the evaluation metrics. So maybe take home message, or I mean, there are all the experts now sitting there, like, I think it's worth a discussion. How can we evaluate our explanations and how can we evaluate the evaluation of our explanation? Thank you.
I think we have time for maybe one question. Do you want to use the mic?
Yes, which are the limitations of these methods? I mean, do you need to use a specific model and a specific architecture, or you can apply it in any model?
Which method do you refer to?
For instance, the global one.
The Dora one?
Yeah, any of that, because sometimes if the network is like dense net or
yes, so actually, like especially for Dora and also for the Bayesian network, you can use any method. So you could also apply this to object detection, for instance. So you're not limited to any kind of model or method.
Okay, so you would recommend Dora, no? Above any of the other methods?
I would totally recommend Dora first in order to figure out where might be potential artifacts learned in your model, because recent work has shown that for local explanation, in order to find outliers, you kind of have to know where to search for, right? And Dora would give you an intuition like, okay, maybe you check those kind of symbols or so, and then you know where to look in your local explanation.
Okay, thank you.
All right, let's thank our speaker again. Thank you, Marina.
Thank you very much.
Arvind, do you want to try sharing your screen while we set up and introduce you?
Hi, everyone. Next, we have Dr. Arvind Satyanarayan. Arvind is an assistant professor of computer science at MIT, where he leads the visualization group at MIT CSAIL. His research uses interactive data visualization as a petri dish to study intelligence augmentation, asking how computational representations and software systems help amplify our cognition and creativity while respecting our agency. He received his PhD from the CS department at Stanford. Dr. Satyanarayan will give a talk on model saliency is an abstraction of model behavior.
Great. Thanks very much for the introduction. Can everyone?
Sorry, Arvind, 1 second. We're just gonna get you our slides up on the screen.
Sure. Hopefully I'm sharing the right window.
Thank you. Yes, you're good to go.
Great. Well, thank you for that introduction, and thank you to the organizers for inviting me. I'm really delighted that venues like this workshop exist, and I wanted to use my talk as an opportunity to build bridges between the way that XAI work is unfolding in the machine learning community and my home communities of human-computer interaction and data visualization. So the work that I'll be talking through today is actually led by 2 PhD students I've highlighted here, Angie Bogust and Harini Suresh. And it was done in collaboration with Hendrik Strobolt at the MIT IBM lab and Professor John Guttag also at MIT CSAIL. So as I was, casting around for how exactly to build bridges between our communities, I felt like I kind of needed a foil, right? An artifact that is well understood between both the ML and the HCI and visualization communities, but one that also provides really fertile ground to contrast approaches. And so as my talk title suggests, what I landed on was saliency methods, right? One of the most commonly used interpretability techniques, typically used to, like we're seeing here, produce heat maps where high valued input features, in this case, bright pixels, are considered to be the most important or influential for producing the ultimate output, which in this case is the prediction of a toy terrier. Now, the reason I think that saliency methods provide a really useful foil is because despite their popularity in terms of their use, as we probably know, the machine learning research literature is full of papers like the ones that I'm showing you here that very rightly call into question the accuracy and the reliability of these saliency methods. But as an HCI researcher, what I find interesting about these papers is their choice to frame their evaluations in terms of these sanity checks, right? Which to me suggests that if a saliency method is failing a sanity check, then we should probably not use it whatsoever, right? Or put another way, this framing of saliency checks or sanity checks suggests that the evaluation criteria that is being tested for is always desirable. And more so that there likely exists some sort of ideal method that passes all of these sanity checks, and we should consider discarding model saliency altogether if they do not. Now, like I said, coming from HCI and visualization, I'm not really used to thinking in this way because HCI and Viz are fields that are rooted in design, and the crux of design is really about navigating trade-offs. Because in the sort of timeless words of the Rolling Stones, you can't always get what you want. Or put another way, my co-authors and I were wondering whether, rather than expecting there to be an ideal saliency method, would it instead be more useful to think about saliency methods as computational abstractions that necessarily need to make particular trade-offs? And so as I was sort of kicking the tires of what it meant to think of saliency methods as computational abstractions, of course, the first place I turned to was, the definition of an abstraction in computer science on Wikipedia. And I swear to you, I'm not making this up, but right on the sidebar was this quote from my co-author, John Guttag. And that's not why we asked him to be a co-author. John is a fantastic researcher, but I really like the way he sort of defines the essence of an abstraction as preserving information that is relevant in a given context and forgetting information that is irrelevant in that context. And this is a really clear, crisp, and simple definition that John uses here, because it succinctly identifies 2 stakes, in abstraction design. The first is, that context is key. Right? And there's likely not the case that for most problems, there's a sort of one-size-fits-all correct abstraction, but rather when an abstraction is right, depends on things like who's using the abstraction, what is it being used for, what knowledge are users coming in with, so on and so forth. Now, unfortunately, this won't be the focus of my talk today, but I refer you to this paper that Harini Suresh and I wrote a few years ago that was presented at ACM Chi 2021. And what this paper does is just propose a richer way of talking about the context in sort of interpretable machine learning, particularly focusing on the users, their needs and knowledge, as well as their goals and objectives when it comes to explainability. Instead, for this talk, I'll focus on the other key idea that John brings up in his quote, the preservation or forgetting of specific kinds of information. And the bulk of this talk really comes from work that we just presented at ACM Fact last week. And so, as we were trying to get a handle on how to describe and evaluate what information saliency methods choose to preserve or forget and how they do it, in ATI, there are several sort of methodological approaches available to us. We can, taxonomize the space or produce a typology or other kinds of ontologies. But really, the one that we favored is an approach called a design space. And a design space is importantly different from a taxonomy or typology because it's not about putting individual methods into particular categories or classes, but rather you're doing the sort of structural analysis to figure out, what makes up the individual instances that you're analyzing. And the goal here is to identify a cross-cutting set of properties or vocabulary or dimensions of the design space that describe those individual points. And what you're hoping for is to get a really minimal, tight set of these dimensions or vocabulary where that minimal set spans as broad a space as possible with as little overlap between the terms. And the reason this matters is because design spaces are most useful when we're thinking about how to compose and combine the vocabulary together, because that process of composition reveals a lot of really rich information about the design space. For instance, we can situate individual methods in the space and compare them, making more precise, identifications about trade-offs and tensions and things like that. And we can also use the design space to identify gaps that exist in our sort of research and knowledge and identify sort of future opportunities for future work. So naturally, the first place to start thinking about is how do we define this vocabulary? And right now, if I was to slightly caricature the vocabulary available to us, I'd say that we roughly talk in terms of how faithful a saliency method is to the underlying model, right? But faithfulness is, I would argue, a pretty blunt tool. It can mean a lot of different things depending on the context. And it's not really descriptive in helping us understand the trade-offs or tensions that might exist when we contrast those individual methods. So instead of faithfulness, what we can start to do is iteratively break apart this whole process of computing a saliency. So we can start by just zooming in on the saliency method more precisely and describe aspects of the methodology it uses to compute the saliency values. For instance, we could describe the impact that a method's hyperparameters have on output saliency. Here, for instance, I'm showing you the output from integrated gradients, where you have to make a choice about the baseline, right? Either 1 or 0, white or black. And they can have a pretty dramatic impact on what the saliency looks like to the user, and then as a result, what sort of insights or implications the user reads into it. Another example of methodology might describe the time and resource costs associated with computing a particular saliency method, from very efficient methods like guided backprop all the way through to methods that are relatively more computationally expensive like line. You can start to get a sense how a dimension like computational efficiency allows us to really, express saliency methods along a particular spectrum. And one that I find particularly interesting, in a place where I think future work can really help us bring more precision, is this idea of semantic directness, or how intuitive is the specific way a method chooses to abstract its information. And this idea of semantic directness, we drew inspiration from really foundational ideas in HCI around direct manipulation, where the idea with direct manipulation is you want to have a really narrow gulf between a user's expectations in their head and how the system actually operates, because the narrower the gulf, the higher your usability of the particular interface that you're trying to build. So for instance, we might say that, LIME, which computes a local surrogate model trained to mimic the original model's decision boundary, introduces a level of indirection that isn't present in another method like SIS, which simply computes the minimal set of features necessary for the model to make its prediction. Now, these are only just some of the descriptors of methodology that we propose, and our paper enumerates several others, including whether or not a method is deterministic, which could be of particular importance to users, or whether or not a method is model agnostic, right? Is it coupled to a particular model architecture, or does it treat that as a black box and only operate off of the input and output? So those are all of our methodological descriptors, but we can also start to break apart the rest of this pipeline, right? So rather than just having the output saliency as a visualization, we could break it apart into the actual sort of computed values, some visual description of those values. And then, of course, we want to include the user in this loop because it's the user that has to interpret and make sense of these values. So with this more expanded view of the process of computing a saliency, we can identify some additional vocabulary for our design space. For instance, we might talk about the more familiar example of sensitivity, right, which many of those papers I showed right at the start grapple with. And even with something as well trodden as sensitivity, there's important nuance that we can find here. In particular, we can identify that users might care separately about the sensitivity of the input features versus the sensitivity of, changes to model parameters or model compression or things like that, or sensitivity of, changes to the output label. So the degree to which you might change the level of abstraction associated with the output label or things like that. And then the last set of vocabulary terms describes the tail end of this saliency process. And we call this category perceptibility, or what is the impact of the method's choices on a person's ability to perceive and interpret the saliency values and the visualization. Now, like the other two categories, we can break perceptibility down into more granular terms. And in particular, we've identified two. The first is a notion of minimality, or how focused or diffuse is the saliency, right? How noisy might it be? For instance, like we're seeing here, vanilla gradients is known to produce a really noisy output, whereas other methods were specifically developed to have a more focused sort of feature attribution being computed. And what's interesting about minimality is it doesn't have to be a purely descriptive measure like I'm describing right now, but the literature does have tests that we can use as quantitative evaluative metrics for minimality, including whether or not the salient features are the smallest set of features that the model can use to make a confident and correct prediction, or the ratio between the minimum and maximum saliency values, and using that as some sort of test. Now, in addition to minimality, we're also introducing this term of perceptual correspondence. And what perceptual correspondence is trying to get at is evaluating not only the visualization used to depict the saliency values, but also the degree to which that visualization aligns with or helps a user build a mental model of what is being shown. And here too, we don't have to be, purely descriptive. We can rely on quantitative evaluations like testing the luminosity of two features in the saliency map and determining whether that is equivalent to their relative impact on the model's output. Or we could do, higher level semantic things like figuring out the degree to which there's overlap between the salient features and some sort of human annotated ground truth. And so if I was to zoom out, right, we've broken that idea of faithfulness, that pretty blunt and overarching term, into these 10 more granular vocabulary terms. And now I think is where the fun actually starts, because we've done all of our definition building, and now we can start that process of composition to figure out how can this vocabulary really help. And to figure this out, we actually interviewed 9 users of saliency methods. And they included, a pretty diverse set of people, including 3 folks who develop saliency methods themselves, 3 more general machine learning researchers, and then 3 users who we kind of categorize as end users, right? They're not affiliated with machine learning in particular, but they use machine learning models as part of their work, whether it's in consulting, computational biology, or radiology. And we started these interviews by actually asking users, how do they think about saliency methods right now? And what we found was that users pick their methods in pretty unprincipled ways, and they're actually quite dissatisfied with these ways. For instance, several users reported picking saliency methods just because they were easy to implement, or because they were frequently cited in the literature, or really it was just the one that they'd heard of, right, based on word of mouth. But as they worked through the dimensions of our design space, they began to more naturally map their the vocabulary of the design space to their task-specific needs. For example, one of the machine learning researchers we talked with iterates through a lot of CNN models and uses saliency methods to compute aggregate statistics of their model performance. So as a result, they considered computational efficiency to be one of the most important properties a saliency method could provide, and then downranked others like model agnosticism, because they didn't care, right? They're only working with CNN models. In contrast, and very interestingly, another machine learning researcher we talked with studies fairness of machine learning models, actually reversed this ranking. Right? So as they evaluate, this person evaluates a diverse range of models, including linear regressions and random forests. They really did need methods that were model agnostic. But for each of these models that they work with, they're only, evaluating handfuls of saliency maps at a time. And so they were willing to pay a higher computational cost if that method was giving them, model agnosticism. Minimality was another dimension that proved to be quite contentious. So the computational biologists that we talked to really prioritize minimality. And the reason is because this biologist trains machine learning models on long chains of amino acid sequences. And then they hand their models off to biochemists to actually interpret saliency values and confirm that the models have learned biologically meaningful features. Now, if they weren't using a minimal saliency method, that validation process would require biochemists to analyze interactions at the scale of hundreds of chains of amino acids, which just doesn't scale or feel feasible in their particular context. Interestingly, we've got the saliency developer felt that minimality was actually not that important because they were worried that minimality might actually hide some spurious correlation in model decision-making. And the radiologist explicitly preferred less minimal methods because they were accustomed to using medical imaging devices that often produce very noisy sorts of output. And so they were very comfortable with and accustomed to interpreting that noisy signal. Finally, even with something like input sensitivity, which is often cited as a sanity check, right? Something that every saliency method should be robust to, we found that didn't universally hold true across all participants. For example, the third machine learning researcher we talked to regularly tests models by perturbing, background features. So without input sensitivity, a saliency method could incorrectly assign importance to changes that the model considers to be unimportant. And in contrast, our second saliency developer didn't care about input sensitivity at all because they only use in-distribution data and don't worry about things like noise or perturbations affecting the input. And so the takeaway for us really underscored the fact that, there is not a one-size-fits-all solution when it comes to saliency methods. Rather, the design space gives us a way to think about the relative strengths and weaknesses of each method and how these strengths and weaknesses may or may not matter for a particular user's context. Now, we can make these relative strengths and weaknesses much more explicit by documenting methods via saliency cards, a form of documentation that we were inspired by datasheets and model cards for. Now, as you can see on the left-hand side, each saliency card enumerates all of the design dimensions that I've been walking through and provides a short description for each one. And for dimensions that can be quantitatively evaluated, we also have a little icon to indicate, in green, whether it successfully passed the evaluation or not in red, or whether, in yellow, the results were inconclusive. And what's interesting about documenting the methods in this way is that we can start to situate and compare individual methods in the overall design space. So for example, if I put the saliency cards for GradCam and integrated gradients side by side, I can quickly see that GradCam, right, has a lot more green associated with it, which suggests that, it appears to be more robust and thus less sensitive to changes in the model, model parameters, model compression, things like that, than integrated gradients appears to be, at least initially. And what's interesting is I can actually scale up that sort of analysis, right? By doing these sorts of comparisons across the entire design space, all the dimensions as rows in this table, and all the saliency methods that we were able to find as columns, we can actually comprehensively survey the research landscape to identify opportunities for future research. So the most obvious thing that pops out here, right, is that there are a lot of gray cells. And the gray cells indicate, areas that a method has not been evaluated against a particular test. And so, suggests an opportunity for maybe a shared, benchmarking platform where new saliency methods, as they come online, can just automatically be evaluated against a battery of these tests to understand where it falls in this landscape. The design space also helps us identify that perceptibility is, far less well tested than sensitivity, right? Far fewer rows associated with perceptibility. And I think there's maybe really interesting opportunities here for machine learning, HCI, and visualization to kind of connect on that methodological piece of how do we actually start to, quantitatively evaluate the impact of perceptibility of various saliency methods. And finally, if we were to sort of zoom in on individual points, we might see that, there appear to be sometimes pairs of dimensions like computational efficiency and model agnosticism that might be in tension with one another, right? So GradChem and integrated gradients, have a lot of computational efficiency at the expense of model agnosticism, and the converse is true with Lime and SIS. And a question that future work might grapple with is, is this just sort of serendipitous? That's just how, the research is unfolded right now? Or is there actually a fundamental trade-off between computational efficiency and model agnosticism? Or is this just an unexplored point in the design space, and this could be something that future work really seeks to prioritize, getting both computationally efficient and model agnostic methods? Now, we intend for this, design space and the saliency cards to be living artifacts, by which we mean that, our definitions for all the attributes, we don't think that those should be fixed, right? As we better understand users' needs, we might bring further definition. We might, rearrange definitions in the design space as new saliency methods come online. We'd hope to see cards added. And so, all our work is on this GitHub repository, and we very much welcome, contributions to it. And in my last, remaining couple of minutes, I wanted to return to that idea of model saliency being an abstraction, right, of model behavior. Because the interesting thing about computational abstractions is that they don't have to be things that only people interact with. Right? For the most part, when we think of saliency, or at least when I think of model saliency, the first thing that comes to my mind is a saliency map, right? But the interesting thing about computational abstractions is that programs can reason over them as well. And in the case of saliency, it means that rather than just visualizing the saliency, we can also start to, think about ways to more automatically compute the ways in which saliency aligns with human annotated ground truth. And in particular, if we've got saliency and ground truth features, we can compute different forms of coverage, like a ground truth coverage that is somewhat analogous to the idea of recall, right? It represents the proportion of the ground truth region covered by the explanation region, or how much of the ground truth does the model incorporate it in its own prediction. We could also calculate a saliency coverage that measures how strictly the model relies only on ground truth features. And this is kind of analogous to precision, right? It represents the proportion of the salient region covered by the ground truth region. And we could also compute, basically an intersection over union, which is the strictest metric that this paper is proposing from this sort of overlap. And it basically measures how aligned the model's behavior is with human reasoning. And we call these metrics shared interest because it's basically measuring, that sort of human AI alignment. And what's interesting is that by computing that sort of overlap, we actually were able to identify across computer vision and NLP 8 different kinds of patterns in model behavior, including when the model was either making a decision or being confused by contextual content, or when the model was attending to only a subset of ground truth features, and whether the subset was sufficient or insufficient for a correct classification. Now, what's interesting about turning saliency and layering an additional set of metrics on top is that we no longer need to think about saliency maps as being these things we have to read one by one by one, but rather something that we can do interactive visual analysis at sort of scale. Right. So here, we're showing you a system that we built to evaluate a melanoma detection model. And we actually worked with a board certified dermatologist to understand how they would use an interface like this. And rather than analyzing saliency maps ad hoc one at a time, they started to use the histograms on the left-hand side to brush and filter, create widgets to sort. And in particular, as they were going through this, they made this really interesting observation about whether or not the model was starting to see things in this sort of context-dependent case. That was something that we, as clinical dermatologists, were not appreciating in the clinical image. And maybe there's something really subtle here that we don't understand that the model does. And so we find that to be sort of a pretty exciting insight that the dermatologist was able to leave with, because we were starting to treat model saliency not just as an output visualization, but as a computational abstraction. And so with that, I'm very happy to take questions about any of this. Thanks very much.
Arvin, can you hear us?
Oh, I can hear you now, yes.
All right, great. Anyone have questions? Okay. I'll first read the question on Zoom, and then we also have another question from an in-person attendee.
Great.
So the first question on Zoom is, if a saliency map does not align with a ground truth annotation, how do we know whether the problem lies in the model or the saliency method?
Oh yeah, great question. So I would say that, if things don't align, that's precisely where I would hope to have, a human in the loop to start to debug why, right? So you might not necessarily just assume the problem either lies with the model or the saliency method, but rather if there's that sort of mismatch and you're able to identify it kind of recurring across different input instances in your data set, that's now a prompt for further analysis, right? So maybe you could try alternate saliency methods and see whether that overlap or lack of overlap still persists. And if it still persists for a variety of saliency methods, right, then that might suggest that the saliency method you used originally was the cause of the misalignment. But if you try a whole bunch of saliency methods out and find that they continue to be misaligned with the ground truth annotation, then that might suggest, maybe you want to start investigating, your modeling choices. Great question.
All right, let's do one more question. Hello, can you hear me?
Yes, I can.
Great. So it was a fantastic talk. I'm Songmin, a PhD student at Georgia Tech. And yeah, it was so interesting. And I'm also a big fan of model salience methods, but at the same time, I was curious if there's any specific reason why people are fascinated by salience methods. I mean, even though there are a lot of other explanation methods like concept-based methods, I think many papers are more focusing on salience methods and checking the sanity rather than other methods.
Yeah.
So I was wondering if there's any specific reason why other research, including yours, is focusing on the salience methods, or if your method can be easily extended to the others.
Gosh, what a fantastic question. Thank you. I was tempted to title this talk in defense of saliency methods, and it's not so much that I have a principled reason for preferring saliency methods or things like that, but I think they're valuable for that point of semantic directness that I was talking about earlier, right? Where, some of the alternate methods that a lot of folks are thinking about, you have to sort of work through multiple layers of indirection, if you will, to really understand what it is the particular interpretability or explainability technique is trying to compute and then trying to depict to you, right? And each point in that indirection process introduces not necessarily more ambiguity, but demands more expertise of the end user. And I think one of the reasons model saliency is proving to be so sticky or salient, if you will, in the research literature is because, it just has the slightly more direct representation to input features, right? So in the case of images, you can just see, brightly lit parts of an image and start to, very rapidly, interpret what is going on for positive and sort of negative reasons. So what I was trying to sort of, explain in this talk was, thinking of things in terms of abstractions is all about trade-offs, right? It's not just at the level of, which saliency method should win out or not, but to treat model saliency altogether as something that shouldn't be the one and only interpretability technique that we, hang the rest of the field on, but rather saying it's one of very many things that you might want to show as part of some, interactive user interface when someone is trying to understand what is going on with the model. So let's not throw the baby out with the bathwater either.
Okay, great. Thank you. All right. Thank you so much, Arvin.
Absolutely. Thanks, everybody.
Okay, so we're going to move on to our spotlight session. Our first speakers here, just give us a minute or two to get set up, and then we'll just get started.
And now should I unmute myself and do the video? No, just start the video on that. And then okay, but so I just take only care of the slides on this laptop. Yeah. Okay.
Sorry, what was it? How do you?
Can you start the video on that one?
There's a video? Oh, the Zoom. Okay. Okay, we can do that. But you want to use it on site?
I don't care. I can put it on the side.
Are you sure?
If the video is here, yes.
You can also do the video there. You can do that, right?
Oh, yeah. But now if it's already working, I think it's fine.
Okay.
Otherwise, yeah, let's not change the working system.
Sure.
Okay, this working? Yes, fine. Thanks. Can everybody hear me? Yes. Okay. Hi, everybody. I'm Sebastian. I'm a PhD student at the University of Tübingen. And fittingly, this talk is also about saliency maps. And the idea is to pitch a really simple idea. But let me first motivate the problem. So we have already talked about this famous paper, Sanity Checks for Saliency Maps. And what the idea that this paper proposed is that a saliency map might look really great, but not be related at all to the model. For example, because it is just like an edge detector. On the other hand, it's actually also possible to come up with saliency maps that are highly related and sensitive to the model, but these saliency maps, they don't look like anything at all to humans. They are just some random pixels in the image that are salient for the model. So this talk is about the second part. And what I want to ask is, what makes a saliency method look like something to humans? Okay. And so in 2019, in the context of robust models, researchers proposed this idea of perceptually aligned explanations, okay? And what was the idea? What they observed in this paper is that standard model gradients, they often usually look like nothing to humans. They are not visually structured. But the gradients of robust models, they have a lot of structure. And so I want to piggyback on this term of perceptually aligned explanations, okay? Basically, like in the saliency map or the local explanation, there is structure that makes sense to humans, okay? Now, I come from a theory group, and the question that I want to ask in this project is, this visually structured to humans or perceptually aligned with human visions, like, can we formulate this, like, formally? Like, can we say mathematically, what does it mean, right? And I want to propose the idea that we can do this. And I want to propose the idea that feature attributions or local explanations are perceptually aligned if they are aligned with the tangent space of the image manifold. Okay, so let me quickly outline the motivation behind this hypothesis. So it's kind of a long-standing hypothesis in computer vision that image data concentrates around a low-dimensional image manifold. Okay, and I want to propose the idea that changes along this image manifold, they correspond to meaningful local perturbations of the image, okay? That would again lead to other natural images and thus correspond like to natural local changes in components of the image, okay? On the other hand, like directions that are not aligned with a tangent space, like the tangent space is like the form of the image manifold, sort of they correspond not to natural directions. A human could not interpret them, okay? And like, for example, random noise, if I just draw a random vector, it lies orthogonal to this manifold. Okay, but now the question is, of course, how can we evaluate this? And here the main challenge is that usually we don't know the image manifold, right? Like we don't have directly access to it. So what we need to do is we need to come up with some simple testing framework where for some simple image data sets, we can reasonably well estimate the structure of the image manifold and then test does perceptual alignment correspond to alignment with the manifold. Okay. And I'm now going to briefly go over 4 pieces of empirical evidence. So here, what we can do is we can take different kinds of explanation methods, and then we can decompose it into 2 parts. And we can decompose it one part that lies in the manifold and another part that is orthogonal to the manifold, okay? And here in the second row, we see the part that is like lies in the image manifold. And the third row is what is orthogonal to the image manifold for given explanation methods. And I would say, at least here in this simple example, we have quite nice intuitive evidence that directions along the manifold, they are natural, and directions orthogonal, they are not. Okay, second piece of evidence that actually is kind of nice. In comparison to the gradient, different kinds of post-hoc methods actually tend to align the explanations with the image manifold. Okay, so we find that post-hoc methods implicitly they have this property of giving us directions that are aligned with the image manifold. And this is not the same across all data sets. Yeah, so like, but this is something by which methods could be evaluated also. Okay, and third kind of evidence, like I began with this motivation of the perceptually aligned gradients from robust model training. So actually, it's interesting to see that robust model training, adversarially robust training, which leads to these perceptually aligned explanations, also leads to explanations that are very aligned with the image manifold according to our evaluation criteria. Okay, and then 4, we also conducted a small kind of user study where we just presented the users with different explanations and asked basically which one looks visually more structured. And we find that users rate explanations as more structured that are more aligned with the manifold. Okay, sort of, again, to wrap up, sort of we are proposing the simple idea visual alignment corresponds to alignment with the image manifold, and we can find reasonably good evidence for this on simple data set. Thanks everybody for your attention.
Any questions?
Hi, very nice idea. How do you parameterize the manifold of images?
Yes, great question. So we train an autoencoder, and then the dimension of the latent space of the autoencoder corresponds to the dimension of the tangent space. Exactly. So, and then there are different like technical things that we could do. Like I'm happy to talk about more at the poster.
Okay.
Yeah.
Thank you.
We have time for one more, if anyone has a question. All right, then let's thank our speaker again and then move on to the give us a minute. The second talk is recorded, although the author, I believe, is live on Zoom to answer any questions. So let me just set that up.
Representing a word hierarchical explanation for regression.
Okay, I'm going to start the talk for the second spotlight.
Hello everyone, this is Sada, and I will be presenting a word hierarchical explanation for regression.
Oh, sorry. I need to share it on Zoom as well. I thought I was getting better at this. Okay. Look at this one. Deeply, is it this one? No. I'm gonna share this one.
I think when you go back to the video,
Yeah.
hit escape. Right now it's blind. It's blind.
Is it this one?
This one.
Is it showing on Zoom? Okay.
Conclusion. I will begin with the motivation.
Sorry, it's just taking time, but
Oh, I don't know what to do then.
so I'm gonna try hitting escape. And then try to reshare just this.
I can't see. Which one is it?
Yeah. Resume share like this.
Do I do this? And then I also just do mirror display. Yeah. Are you all set? Okay.
Hello everyone, this is Sada, and I will be presenting a word hierarchical explanation for regression recognition. I will begin with the motivation behind this work. So in this work, we are inspired by the way humans explain their decisions. So we humans, we tend to explain our decisions on different levels of granularity based on the information that we have. If we have less information, we are more abstract, and if we have more information, we tend to explain more concretely. So, for instance, if we see a crowd cheering in a video, then we might infer it as a sports event. As the video progresses and we see a playground and some targets, then we might infer it as a target sports event. And when we see players with their goals, we conclude that this is an archery competition. So in this work, we are inspired by such way of explanations. I will go over some related work, and as we all know that majority of the research in the domain of explainable AI focuses on explaining networks for images, while there is very not a lot of work for interpretations for videos. So I will introduce two of the related works. One is called class feature dynamics for video explanation. So in this work, the model explores each layer and tries to find the kernels responsible for classification, while the second work is utilizes perturbations for providing explanations. So they perturb input video and try to figure out which part of the input was responsible for a specific classification. So, however, both these methods are post-hoc methods and are single level, while in our work we work on built-in explanations and also provide hierarchical different levels of explanations. And our work falls into case-based reasoning models. So there are two major categories of case-based reasoning models. One is concept bottleneck models, in which you introduce a bottleneck layer, mostly at the end of the network, which predicts human understandable concepts like green color, undertail color, and then you use those concepts to perform classification. While in prototype-based models, you learn prototypes which represent training samples, and perform a classification based on those prototypes. Our work is focused on prototype-based models. And as we introduce hierarchical explanations, so the way we integrate hierarchies in our network is by using hyperbolic embedding space. So different from Euclidean space, hyperbolic embedding space represents hierarchical knowledge in the embedding space. So its continuous representation enables implicit inclusion of parent and grandparent classes, along with the child classes, which we usually have in Euclidean space. Next, I will go over the method. So in this, the way we do it is we begin with a ResNet 3D backbone and extract video features, and then we introduce a hierarchical prototype layer. And over here, and this prototype layer learns prototypes for children classes, for parent, and also for grandparent class. For example, here the child classes are line diameter file, for a parent is self-grooming, and a grandparent is human object interaction. Then we convert these prototypes into similarity scores, which represent how similar these prototypes are with the extracted features from ResNet. At the same time, we also have class embeddings embedded into a hyperbolic space in order to learn these hierarchical prototypes. So we embed class embeddings, or in case of we use actions into embedding space, hyperbolic embedding space, which represents these embeddings in hierarchical form. As class embeddings are in hyperbolic space and video embeddings are in Euclidean space, so we need to convert them into same embeddings. We need to map them into same embedding space in order to learn, in order to perform learning. So we use exponential map in order to convert Euclidean features into hyperbolic space, and then we use hierarchical cross entropy laws to perform the classification as well as to learn hierarchical prototypes. And this is a bit more in detail explanation of how we learn the hierarchical prototype layer. So we use given convolutional features from convolutional network, we compute the distances between the prototypes and the output from the convolutional layer, and then finally convert them into similarity scores. And these similarity scores represent how close a prototype is to the convolutional output. And in order to provide visual explanations, we project these prototypes onto the closest video features from the training videos, and then we visualize them. And we do so for the child, parent, and grandparent classes. And now experiments. So we conducted our experiments on UCF 101, which consists of around 13,000 videos belonging to 101 classes action categories. And the data set also comes with 5 grandparent categories, like major categories like playing music or human object interaction. But we define 20 parent categories here. For example, target sports, water sports, ice or snow sports, and these are defined using by grouping the action classes. And we evaluate our method using accuracy, and also as we are in hyperbolic space, so we can also calculate signal accuracy and also person accuracy, like the relatedness. And the top 2 networks are non-interpretable networks in this table, and the last 2 are interpretable. And we observe that when we make these networks fully interpretable, the performance drops, while our method tries to recover it, which shows the effectiveness of our method. Now, some qualitative results. So this test video, the top 1 prediction for this video is blow dry, and this is one of the learned prototypes for this class. We learned 10 prototypes per class in our method, in our experiments. And the top 2 prediction, we observe that usually if it's the Euclidean space, then it's possible that the second prediction will be by random, while here this top 2 prediction is the sibling class. And these are the prototypes learned at the parent level, and these are the parent level class which is self-grooming, and these are the prototypes learned at the grandparent class. This shows explanations in the case of failure in classification. So this one scheme video was misclassified into rock climbing indoor, and obviously the learned prototypes belonged to rock climbing indoor. That's why it's misclassified into rock climbing indoor class. However, we observed that the parent class and this rock climbing indoor is basically a sibling class actually. and it's not misclassified into a completely different class. So the parent class is still sterness force, and the front parent is body motion class. So to conclude, in this work, we enabled multi-level explanations, which provide more information rather than just explaining only the categories with child categories. And our quantitative results showed that our method reduces explainability trade-off. And yeah, we introduced this for in order to provide some explanations for videos. Thank you.
Any questions for the speaker?
Hello, everyone. This is Farooq, and
No questions? Anyone? Okay. All right, then we're going to move on to the second spotlight. If you have any questions, feel free to reach out to the authors directly. The third spotlight. This one's also pre-recorded, so I'm going to play the video.
Hello all, I'm Syed Numan Hassani, and I'll be presenting our project SegXScam, explaining spatially local regions in image segmentation. The other two members involved in the project are Claude Petitjean and Fabrice Mariano. Attribution-based post-hoc methods have been quite popular in explainable AI. However, most such methods have been presented in the context of image classification. Some methods have been extended to other tasks like image segmentation. One such method is SegGradCam, an extension of GradCam to image segmentation. In the present work, we show that by virtue of its formulation, SegGradCam does not perform well when it comes to generating attribution maps for a target class in a region of interest as compared to the entire segmentation map. Taking inspiration from Hierarchical, we propose SegXScam, which takes spatial information into account when generating region-specific attribution maps. In image classification, attribution-based methods can primarily be divided into gradient-based versus perturbation-based. The method on the left is a gradient-based technique which simply visualizes the derivative of the output with respect to the input image. The method on the right is a perturbation-based technique which generates an attribution map by masking the image multiple times and then taking a linear combination of those masks. In image segmentation, grid saliency is one of the earliest works about generating attribution maps, and it utilizes a perturbation-based technique to try and learn the necessary context for a segmentation. On the right is U-noise, which tries to learn a model which can directly predict an attribution map given an input image. Now, a conventional computer vision model for classification is a convolutional architecture incorporating convolutional layers followed by a couple of fully connected layers. For example, if the following image is presented to the model, it assigns the highest score to the waterfall layer. Now, if we want to generate an attribution map for this image, GradCam provides us with a simple mechanism to do that. We first pick a layer to analyze, generally the layer just before the fully connected layer is chosen. GradCam generates an attribution map by taking a linear combination of the attribution maps of the selected layer. We now need to find the coefficients of the linear combination. In GradCam, an individual coefficient is obtained by taking the global average pooling over the gradient matrix representing the derivative of the target score with respect to the particular activation map associated with that coefficient. Once we have found all of the coefficients, we can generate our attribution map and overlay it on the original image to see. A conventional computer vision model for segmentation consists of an encoder, a decoder, and a bottleneck layer between the two. Now, for example, for the following input image, the image segmentation model returns a segmentation map highlighting all of the cards. If we now want to generate an attribution map for this image, we can use SegGradCam, which is an extension of GradCam for segmentation. Once again, we first need to pick a layer, and it is common to pick the bottleneck layer. Similar to GradCam, SegGradCam generates an attribution map by taking a linear combination of the activation maps of the selected layer. Now we need to find the coefficients of the linear combination. In SegGradCam, we first select a set of pixels which belong to the target class, and this is our region of interest represented here as M. Now we sum up the scores in this region, and any individual coefficient is obtained by taking the global average pooling over the gradient matrix representing the derivative of the sum with respect to the particular activation map associated with that coefficient. Once again, once we find all of the coefficients, we can generate our attribution map and overlay it on the original image to see. Now, what if we don't want the attribution map explaining all of the cars and we only want the attribution map for the leftmost car? We can once again calculate our linear coefficients, but this time our region of interest is only the leftmost car. However, our final attribution map seems to be highlighting all of the cars as being relevant to our prediction of the leftmost car, while we might at least have expected the leftmost car to be the most highlighted. If we repeat this for the third car from the left, we once again find that Selective highlights all of the cars as being relevant. It does not extraordinarily highlight the car under consideration. In fact, if we observe the attribution maps generated by Selective for all of the cars versus individual cars, the maps are almost identical. So what is happening here? If we consider the case of all cars versus the leftmost car, the formulation of our final attribution maps is going to be as follows. In both cases, a linear combination of the activation maps. Now, the activation maps in both cases are the same. The only thing different in the two cases are the linear coefficients which carry the information provided by the derivative of the sum of scores. However, because each activation map is assigned a single scalar coefficient, the spatial distribution of the activation map plays no part in the eventual linear combination, as all spatial locations in the activation map are scaled uniformly by the linear coefficient. This is why even when we only want to generate attribution maps for the leftmost car, there is no way for the linear coefficients to particularly highlight only the region surrounding the leftmost car, and hence they end up highlighting all of the cars. A potential fix for this is to instead utilize another method proposed in the context of generating attribution maps for classification, that is Hierarchical. In Hierarchical, instead of taking the global average pooling, the gradient matrix is lengthwise multiplied with the feature maps, hence ensuring that the signal present in the derivative impacts different spatial locations accordingly. If we look at the maps generated by utilizing Hierarchical instead of GradCam, we can see that Hierarchical only highlights the leftmost car as salient as opposed to GradCam, which highlights all of the cars. Further corroboration of this attribution map is achieved when we utilize RISE, which is a model agnostic perturbation-based method in order to generate the attribution map. And it also only highlights a region focused on the leftmost car. We can further generalize the formulation of Hierarchical in order to control how fine or coarse we want our gradient signal to be. We can do this by first applying pooling, followed by aggregation happens. In this way, by controlling the pooling window size, we will arrive at the results of Hierarchical on one end of the spectrum and arrive at the results of GradCam on the other end. One way in which these attribution maps can be analyzed or evaluated is by utilizing them to mask the image, followed by getting the model's prediction on the masked image. We can compare the model's prediction on the masked image versus its prediction on the original image in the region of interest, and we can do this using dice. Additionally, we can also note the percentage of the image preserved by our attribution map. As we can see, Sec-XResCam retains a smaller portion of the image and still gives a better dice than SecGrad. To conclude, we have shown that by virtue of its formulation, SecGradCam does not take spatial information into account when it comes to explaining a target class in a region of interest. A potential remedy is to utilize Sec-XResCam, which is a generalization of SecGradCam and Sec-Hierarchical, and it takes spatial information into account when generating its attribution map. Some questions for future exploration include the choice of layer, because here we only focused on the bottleneck, as was done by SecGradCam, and also an extensive quantitative comparison between Sec-XResCam with some of the perturbation-based methods like RISE. Thank you.
So I don't believe any of the authors are here. So if you have any questions directed directly to the authors, their email address and all information is online. And with that, we're going to move on to our poster session. So like I said, it's in West Exhibition Hall, 203-2241. If we can all head there together. and engage with the authors, that would be great. And then if you're interested in doing lunch together, I mean, we can't do it all together, but we'll break into smaller groups. Come back to this room by 12 and we'll head out to the ballrooms together. So yeah, enjoy. And we, the organizers, will also be there in a bit after we clean up a little bit, but have fun at the poster session.
Yeah, no, that's cool. Yeah, it seems like there's some interesting potential intersections for XAI and like the smart climate and animal science work.
I think so. It's something because, on the satellite, there's lots of evidence.
Exactly. It's much harder to do with fine grained visual imaging.
Yeah. Like Saliency maps are, they're not really fine. While there is still research on it.
Hi, everyone. We're going to get started with the afternoon session. I'm really excited to introduce Dr. Mohit Bansal. He's the John R. and Louis S. Parker Professor and Director of the Murgy Lab in the Computer Science Department at the University of North Carolina, Chapel Hill. Prior to this, he was a research assistant professor at TTIC, and he received his PhD from UC Berkeley and his BTech from IIT Kanpur. His research expertise is in natural language processing and multimodal machine learning, with a particular focus on grounded and embodied semantics, language generation, and question answering, and interpretable and generalizable deep learning. He's a recipient of numerous awards, including the IJCAI Early Career Spotlight, the DARPA Director's Fellowship, NSF Career Award, and several outstanding paper awards at ACL, CVPR, EACL, CoLing, and CoNLL. He will give a talk on interpretable image generation and evaluation and right for the right reason explanation supervision. Over to you, Dr. Bansal.
Thanks, Vikram. Thanks, everyone, for having me. And yeah, sorry, I couldn't be there in person end of the day. Let me share my screen. You cannot share while the other participant is sharing. Okay, great. Thanks. Okay, so hopefully you can see my screen in full screen mode.
Yes, we can see everything.
Great, yeah, so I have 30 minutes, so I'll get started and I'll keep some minutes, hopefully in the end for questions too, but I'm trying to cover two parts here, which are closely related to explainability for vision. So this is the first part of the talk where I want to discuss explainable image generation and evaluation. So the basic premise is how can we make the process of text to image generation more interpretable, and meanwhile also allowing more step-by-step spatial control. And then in addition, can we also make the process of evaluating text to image generation, right, which itself is a pretty challenging and understudied problem. Can we actually make that evaluation process also more interpretable, which allows more fine-grained error analysis, but also better correlation with humans for human metric correlation, and at the same time also allowing you to provide visual plus textual explanations of these errors in the generated images. And then the second part will be about how to supervise model explanations. So from the other angle, where if you have, say, visual explanations of regions, attention maps kind of regions for visual supervision of a model making, say, predictions for visual question answering, how can we make sure that the model explanation supervision is meaningful and it's meaningfully improving model accuracy, which means that it's not spurious correlations, but it's right for the right reasons. We'll also see how we can evaluate models on such right for the right reason metrics like sufficiency, uncertainty, and variance. And we'll see what is the reason why this feature importance or FI supervision is improving accuracy. And is it correlation between accuracy versus plausibility or plausibility plus faithfulness? And lastly, we'll try to see some surprising results on whether these kinds of RRR metrics can predict out of domain generalization. Okay, so let me get started in interest of time. So the first part is the visual programming for text to image generation and evaluation, as I mentioned. So the premise is the same thing that I mentioned a minute ago, that in text to image generation, usually there's a single end-to-end model, right, which basically takes a text prompt and generates an image. But ideally, we also want to understand the question that how does the model, how did it decide, right, what to generate, where to generate it, in which order to generate it, right, which modules were called, and so on. And same for text to image evaluation. If I have the generated image, instead of just running a black box evaluation model like CLIP and getting a score, I would like to understand how did this score get computed, what were the exact errors, what was correct, what was incorrect, right? And this also helps you be able to further improve the model. So the background very briefly here goes long way back, right? Even neural modular networks, Andreas et al., CVPR 2016, MATNet, summarization programs, visual programming, Viper GPT, a lot of work has been looking at different forms of situations where the modules are being organized into some sort of graph or program. And it's an interpretable paradigm where can we make sure that we also understand the neurosymbolic graph-based ordering of the modules that was called and was executed in order to get the answer to a certain reasoning question. So most recently, the examples would be visual programming and Viper GPT, right, where you have defined visual modules, and then you use a large language model more recently, right? For example, ChatGPT or Vicuna and others can be used these language models to generate programs on top of these visual modules, right? What modules to call, which order to call them in, how to nest them together, how to do recursion, and so on. And then you execute that program to get the answer to, for example, for VQA. So what we are going to discuss in this slide, in this talk, is that can we use the same framework and adapt it to text-to-image generation as well as text-to-image evaluation. So the first part is called VP-Gen, which means visual programming for text-to-image generation. And then VP-Eval is visual programming for explainable text-to-image evaluation. So let's briefly discuss VP-Gen first. You take a prompt, and then you first basically get the object and count generation. So if the prompt or the caption is 2 Pikachus on a table, then the language model first converts that to Pikachu 2 and table 1. And then the language model, again, which could be Vicuna or ChatGPT in our work, basically also does the second step of layout generation. So given the caption and the objects detected Pikachu 2 and table 1, can it generate the boxes for the 2 Pikachus and the table? And then finally, you use a layout to image generation kind of model, for example, Glygen in our work, to be able to convert, to do layout to image, L2I, to be able to get the generated image. And then for VP eval, it's a little bit inverted, right? So you first have these modules, like I said, which would be different kinds of evaluation modules. So one example would be object detection. A more complex example would be spatial evaluation. So it will basically take the 2 objects, and then it will basically have to make sure that if the target relation is, for example, right, then it will check that the x coordinate of the first or the second object, right, is the greater than or less than the other one. Scale evaluation would have different measures of bigger, so area greater than or smaller, and so on. And then what you would do for VP eval is you will build together these modules using a program for a given prompt and generated image. So the first kind of VP eval is skill-based evaluation. So these are single skill-based evaluation programs. So if you're saying photo of a dog, then the language model automatically converts it to this object eval program. Or if it's 3 dogs, then it will fire the count eval program with image, dog, and then equal to 3 is what it's checking. And then if it's spatial, spoon is in front of the potted plant, then the program fired by the language model conversion should be this spatial eval program. And then on the right side, it also executes that program on the generated image. So on the left side, the generated image actually satisfies that program because it finds the spoon and a potted plant such that the z coordinate of the spoon is less than the z coordinate of the plant, and hence it's in front of, right? Whereas on another generated image, the answer is incorrect because the this pairing of spoon and potted plant with the relation front was not found. Whereas for the count example, this is the correct case because there were 3 objects named dog, whereas in the second image, it's incorrect because it gives you the reasoning that there are 5 dog objects, not 3. And then the more open-ended version of VP eval is what we call open-ended interpretable evaluation program, where you can have several combinations of skills that need to be evaluated. So for example, a very complex prompt could be a white slope covers the background, while the foreground features a grassy slope with several rams grazing and one measly and underdeveloped evergreen in the foreground. So the language model, in this case, ChatGPT, converts this prompt to a set of evaluation modules. So object eval for ram, evergreen, for counting of ram greater than 1, but counting for evergreen is equal to 1. And then there's also a VQA module, which can basically answer what is in the foreground, and the answer should be one of these. And then when you execute that program on the generated image, which in this case is the image shown with my pointer here, it tells you what all of these programs, these skills were correctly found in the generated image versus which was incorrect. So the RAM object was not found. So you see the arrows here, but the evergreen object was found. But then the count part was wrong because it found 8 evergreens instead of 1. And then the VQA part was correct because the VQA model answered grassy slope. So I'll keep the results part a bit brief, but the basic idea with human judgments using, say, Spearman correlation as compared to other metrics like CIDR, SPICE, CLIP, and so on. So in summary, both on skill-based evaluation on the left side and open-ended evaluation on the right side, VP eval gets the highest human metric correlation values. And then for the VP gen, so back to the model, right? So this was the previous slide shows the results on the evaluation metric being better correlated with humans. And then back to the model, which is the VP gen model that basically takes a prompt, converts it to a program, and then gets the layout from the program and then uses layout to image for generation. They're also compared to Stable Diffusion, different versions, Carlo, Min, DALI, DALI Mega, and so on. We see big gains by combining VP gen programming plus a layout to image model like Glygen off the shelf. We see big gains in counting, spatial, and scale based control, while at the same time also having an interpretable program that generates the image. And then we did 2 types of error analysis, both for VP gen and VP eval, but more details in the paper. Just a short version of this is that for VP gen, we discussed in the paper how the Vicuna language model that's generating the programs right before generating the image, on a small scale human study, we find that it can generate the program correctly 92% of the time, but Glygen after that only generates correct images 65% of the time, which is understandable, right? So basically the summary here is that the program could be correct, but then when you feed the layout created by the program to a layout to image model, it can still make its own errors. So we see some examples on the right here. So this gives us some insights for the future work part, right? That you will get, if you have better layout to image generation models in future work, then this should further improve VP gen based results because you can plug in the program based VP gen generation before to any layout to image model. And then on the VP eval side, we also check for coverage and faithfulness. So the left side basically checks that how many of the elements from the prompt were covered in the generated programs. So that's around 94% on a human study. And then the right side covers the fact that it checks the fact that how many of those modules were doing the right job. So they are covered, but then when they get fired, do they do the right thing? So that's around 83%. So again, gives us some nice insights for what's further improvable in next work and future work. Okay, so I think I'm on time. So now let's switch gears a little bit. And the second part of the talk is more about, like I said, how to meaningfully supervise model explanations, right? So this connects to the fact that you can have model explanations, but how do you make sure that they're actually being used in the right way to improve the downstream model task accuracy and not for incorrect reasons, right? So how do you make sure it's right for the right reasons? So this is from NeurIPS last year, 2022. And the problem here, as I mentioned at the beginning of the talk, is that you want to make sure that models are making the correct prediction for the right reason. And you want to do that by telling them what features are important. So this is known as feature importance or FI supervision. But existing FI supervision methods for VQA models can improve accuracy, right? But recent work has shown that this is not sure whether the human supervision is the actual source for these improvements. And by that, what I mean is that specifically Shrestha et al., they took the VQA improvements and they showed that they still persist or exist even when you actually replace the human supervision or feature importance supervision with just random image feature importance annotations. So this suggests that existing approaches may not be extracting meaningful signals from these human annotations. And the way past VQA methods are using these human annotation signals is either through data augmentation techniques or directly supervising the model's feature importance. So instead, we show how we can make use of 4 important right for the right reason objectives to make sure that this human supervision of feature importance or explanations is being used in the right way to supervise model feature importance or model explanations. So here are the 4 key objectives. One is sufficiency, which means that you want to make sure that the predictions are accurate given limited, but only the sufficient information. I'll not go into the details in interest of time, but the basic idea is you minimize cross entropy with label given masked input, where the masking is only keeping the relevant features. Uncertainty is the opposite, where you're trying to make sure that you get max entropy predictions when you're not given any important information. So again, the details are a bit hard to go into for now, but to summarize, you regularize predicted distribution against uniform distribution for masked inputs, where in this case, the masking is keeping the irrelevant features. You also want invariance, that the prediction should not change based on changes to unimportant features. So you get a model feature importance explanation and then penalize any assigned importance to unimportant features for this. And then lastly, plausibility means alignment between model and human feature importance explanations, in this case, the attention maps. So you penalize a distance between human and model feature importance explanations. And the overall objective basically becomes L sufficient, L uncertainty, L invariance, and L alignment get added to the original task objective. And again, you can see the details in the paper, but the idea here is the things I said in the previous slides, that when you have important features, for L uncertainty, you have unimportant masks. And then for invariance, you are adding random features to the important features, and it should not change, right? It should have the same output as important features, right? So important features, accurate output, unimportant features, uncertain output. Important plus random features or noise should be same output as important features. And then finally, this is the one that tries to align models feature importance values with the human feature importance values. So the summary in just one slide is that you have several VQA datasets with ID in domain and out of domain splits, and WisFizz gets big improvements compared to all previous methods as compared to the sufficient random baseline, whereas most of the previous work either gets equal or worse results than sufficient random. And then Singla et al. Is also getting good improvements, but again, not as high as WisFizz with the 4 right for right reason objectives. More importantly, I think the analysis in this work is more interesting. We are saying, why does this work, right? So model explanations, for example, right? The question in your head should be, are not necessarily faithful to model reasoning. So then why should aligning model and human explanations improve accuracy? So this is what we wanted to check in the second part of the paper, where we said we want to check whether model human agreement, which is the plausibility as we defined, right? Or the alignment, does it correlate with accuracy, right? Is that what's leading to better accuracy? But then the important thing we do is we group it by explanation faithfulness, which is measured by previous work's definition of sufficiency and comprehensiveness, where the idea is that if you, sufficiency means that if you only keep the important features, then the confidence in the model prediction should not change. And if you remove the important features, then the confidence in the model prediction should decline. And so this is a surprising sort of result here, where you basically show that no, plausibility and task accuracy are not correlated on their own. They are only correlated when the explanation faithfulness is also high, which is the orange line. Whereas if the explanation faithfulness is bad, then it almost becomes no correlation, the green line. And this is some detailed examples of this in the paper. Again, to very briefly summarize, since we won't have time to go into too much detail, but the idea here is that the x-axis is plausibility. So it's increasing here, and faithfulness is increasing on the y-axis. So as you can see, when faithfulness is high, which is the top part of the plot, then you get basically the plausibility is high and faithfulness is high, right? This is the top right. Then you have good task accuracy or prediction, sorry. But when faithfulness is low, the bottom row, you see the opposite happening, right? Plausibility can still be wrong, but the answer can be correct. Or when faithfulness is low, plausibility can be correct in this case, but the answer can still be wrong. So this is the basic summary of the fact that the correlation of model task accuracy is not just with plausibility, but with plausibility plus faithfulness. So you see what I mean here, right? Because in this case, the plausibility part is wrong, but the prediction is still correct, and vice versa here. So the third part of the results was that we also wanted to make sure that we are not just evaluating on task accuracy, but also right for the right reason metrics. So besides being correct, we also want the models to be right for the right reasons. So for this case, you can define a broad set of right for the right reason metrics. And specifically, in addition to measuring existing metrics, which is in distribution accuracy, out of distribution accuracy, and model accuracy on sufficient feature subsets, which is RRR SUF, we also evaluate on model uncertainty given uninformative inputs, which is RRR UNC, and model invariance to changes in unimportant features, RRR INF. So in summary, these metrics basically help you verify that models can arrive at correct answers relying only on features that are actually important, are invariant to the addition of or removal of unimportant features that should not affect the prediction, and are appropriately uncertain about the model class when input contains no meaningful evidence for any class. So again, results in the paper will show you that WizFizz, the method that we defined, does improve several RRR metric scores, not just the task in domain and out of domain accuracies. And finally, I want to end with a surprising negative result here about these kinds of RRR metrics. So the idea here is that, again, the practical value of RRR metrics should be considered in terms of their ability to inform us about model performance on data that we are not able to test on, right? So the whole idea is that you're not overfitting to some in-domain data, and you should be able to perform well on out-of-domain distributions, right? That's the whole point of sufficiency, invariance, right? All these things, uncertainty that we are discussing. But we wanted to check whether these existing metrics, right? Because, I mean, we also want to make sure that you have these metrics that can help you predict performance on out-of-domain distributions. So if you want to simulate this situation, you compute RRR metrics on in-distribution data for a bunch of models, and then you see if that lets us predict model generalization to out-of-domain data. So again, the summary of the results here, we can't go into the details which are in the paper, but the main negative result here is that these existing RRR metrics actually do not correlate well with OOD accuracy. So in the sense that they are not better than in correlating with OOD accuracy than just in-domain accuracies correlation. So you can actually just use in-domain accuracy as the correlation to predict out-of-domain accuracy. So the main takeaways are that feature importance or model explanation supervision with right for the right reason objectives can improve both in-domain and out-of-domain model accuracy on several VQA datasets. In particular, WizFizz improved over several baselines and previous state of the art by up to 4.7 points on OOD data. And we showed that explanation plausibility correlates with model accuracy only when explanations are also faithful, which sheds light on how FI supervision improves model accuracy, and the correlation doesn't happen with just plausibility. And then FI supervision also improves model performance on several right for the right reason metrics, including the new invariance and uncertainty metrics we proposed. And then finally, if you want to use RRR metrics also as a way to predict whether out-of-domain accuracy will be good, that current metrics yet do not correlate better than just in-domain model accuracy correlates on its own. So you can just use in-domain accuracy to predict OOD accuracy, and you're not going to get better than that by using RRR metrics. So that leads to some important future work discussions on needing better and newer RRR metrics for OOD prediction. So I'll end here and leave a few minutes for questions. Thanks.
Right. We have some time to take a couple of questions. So do we have any questions in the room? Okay. Oh. So we have one in the chat. Were the RRR objectives or metrics sometimes at odds with each other?
Sorry, let me read it once. Oh yeah, that's a good question. So we haven't checked that very directly, but I think we remember seeing some plots where the different sub-objectives, when you plot them, in addition to the overall objective that sums together all of these, they do behave a little bit sort of at odds at each other, right? Because in some sense, sufficiency, like they are defined as opposites of each other. So unless you have the perfect kind of data, right, and you have enough convergence, there will be situations in the beginning where they will be contradicting each other. So yeah, that's a good point. And then in terms of metrics, let me see, I don't remember the exact behavior there. I guess I removed this. Yeah, I remember them being not at odds at each other, but the trends were slightly different. Like if you get the best improvements in one metric, the same model may not be the best at the other metric, but the WISFIS model, because it takes all 4 objectives into consideration, there is no contradiction. It gets improvements on all the metrics.
Any other questions for the speaker?
Okay, go for it.
I actually had one more question, which is, in general, when you're working on multimodal models, I'm curious whether you find that more difficult or easy in some ways for doing like explainability research than, let's say, just NLP or computer vision.
Yeah, so most of our explainability work has actually not been multimodal, which probably answers part of your question. So most of our work has been on the language side, for example, how to generate explanations that don't leak the answer, how to do things like summarization programs, right, where you actually show the generation process as an explainable neural model and network graph. The image generation part of the talk that I showed, right, where we were generating programs on how to generate images, is a good multimodal example. But even there, the input is text, right? The output is not multimodal. So I would still think of it as not purely multimodal, right? The pure multimodal situation would be where the output, right, for example, is both, say, language and vision. And that would be both easy and hard in certain ways. It would be harder because you do have to look at contradictions between the modalities, right? And you also need to have alignment and agreement, which is a big challenge, right? Correspondence. But it's also easy in the sense that we've seen some situations in current, like the work we are doing, where they also fill gaps for each other, right? Because certain modalities will be easier at explaining certain phenomena than the other modality. But yeah, I think the text-to-image generation part is, to me, still not very multimodal, because it's basically taking the text prompt and verifying the faithfulness of the program with respect to the input text, and then converting it to layouts, and then it's pure vision.
Okay. Yeah, if we don't have any more questions for Dr. Bansal, let's thank him again.
Thanks, everyone.
Thank you so much. Okay, in that case, let's move on. I am really excited to introduce Dr. Vera Liao. She's a principal researcher at Microsoft Research Montreal, where she's part of the Fairness, Accountability, Transparency, and Ethics of AI group. She works on human-AI interaction with a current focus on explainable AI and responsible AI. Her research bridges emerging AI technologies and human-centered design practices, and uses both quantitative and qualitative methods to generate recommendations for technology design. Before joining MSR, she worked at the IBM T.J. Watson Research Center and studied at the University of Illinois at Urbana-Champaign and Tsinghua University. Dr. Liao currently serves as the co-editor-in-chief for Springer HCI book series and is the editor and area chair for numerous journals and conferences, including ACM, CSCW, CHI, FACT, and Transactions on Interactive Intelligence Systems. She'll give a talk on towards human-compatible, explainable AI. And over to you.
Great, thanks for the introduction. I'm going to try to share actually part of my screen so that I can see the notes. Hope it works in one try. Okay.
Yeah.
Are you seeing my? Great. Yeah. Thanks for having me. Thanks for the introduction. Sorry I could not make it to the workshop. I hope I can meet some of you, the organizer, the attendee in person sometime soon. So yeah, I'm just gonna jump into it. And I think for this audience, I don't need to talk about the motivation, why we need explainable AI. I want to start with the particular perspective I take. right? So I am a HCI, human-computer interaction researcher by training. Within HCI, we have a growing community we call human-centered explainable AI. We are often interested in how people use AI explanation, studying in specific application, and also the usage often determine people's cognitive process, right? What kind of explanation they want, how to process the information, and the usage and the cognition. By understanding them, we can inform technology development, which concerns not only with the technique, but also the interface. And for this talk, because it's relatively short, I'm going to focus on this cognition part. I'm hoping to provide a bit more principled understanding of how are people processing AI explanation collectively, and hope to provide one path of how we can make XAI more collectively compatible, sharing some of our most recent work. And I'm going to ground this talk in one particular use case, which is explanation for decision maker used in the kind of decision support AI system. So the general setup is if you have a decision task, right? And then you're going to introduce AI system here to make a prediction. And that essentially turn this human decision maker's task into a reliance decision. Should I rely on the model, take the prediction, or should I do something on my own? And whether this reliance is appropriate, right, depend on if the model prediction is right or wrong. And the hope has been that by adding explanation to the model prediction, we can help the decision maker to make a more informed decision, especially to detect model error, to avoid inappropriate reliance so that people will make less mistake and make better decision. But the reality has been quite mixed. A lot of HCI study in this field by conducting empirical study, finding that explanation have this pitfall, this hidden risk that they can lead to unwarranted trust and over-reliance. For example, this is a study that we published at FACT 2020. We did this experiment using a semi-toy example where we asked people to look at someone's profile and guess if this person is a high or low income group. And we find that when show participants this feature importance explanation, their performance actually dropped. The reason is because when having the explanation, it actually increased people's tendency to over-rely on the model when the prediction is wrong. So that increased actually their decision mistake. And we're not the only one finding this observation. There are many other HCI studies finding the same, and also for other tasks. For example, this paper by my MSR colleague, by Keller et al., they find that for data scientists, when they use this kind of explainable AI debugging tool, it also increased their overconfidence that model is ready. Some HCI studies even find that placebo explanation without showing useful information can increase people's trust. And I want to highlight that over-reliance is a serious problem for human AI interaction. It's not just a one-off mistake, right? Making a wrong, unjustified decision can have downstream harm, negative consequence. They can also bring psychological harm to the decision maker themselves, and also raise question about accountability, how we should assign the blame. And the reason is because this kind of explanation may not be compatible with people's cognitive process, right? Many work trying to explain this phenomenon of explanation need to overconfidence by there may be a lack of cognitive engagement. So people process information with this kind of dual cognitive process. You may have read the book, Think Fast and Slow, that we have this slow thinking process to gather all the information and to trying to make a rational judgment. And this is often assumed by this having this kind of ideal user who will pay attention to explanation, carefully reason about it, and understand it. But in reality, real user actually more likely resort to their fast thinking process by invoking some kind of heuristic and rule of thumb. Some of our prior work also find that people have a certain superficial association. When they see explanation, they think the AI is capable and trustworthy. I think this overall framing of explainable AI being this great thing is adding to that. So there's a potential that people don't have a good qualitative engagement, right? Even myself has been using that to explain this phenomenon, but in the back of my head, I always have the question of, is cognitive engagement what we need? Do we only need to nudge people to pay more attention? Or is there a certain inherent limit to what an explainable AI method can do? So to get to there, I want to borrow some term from this paper by Chen et al. I think they published at ICML. They also have a version at FAC this year. So it's a paper that differentiates two concepts. One is model decision boundary, how the model make decision, model assign labels, and task decision boundary, which is about how the decision should be made. What matters is human always bring certain intuition about the task decision boundary, such as if someone is highly educated, they're more likely to make high income. And feature importance explanation can only help people understand model decision boundary. But when people interact with explanation, they're always applying their intuition about the task decision boundary. And it's between the contrast of the two, they're able to detect model errors. So to understand how people use explanation, we have to understand this interplay between explanation and people's own intuition. So last summer, we conducted this study with our former intern, Valerie Chen, who is a PhD student at CMU. So we try to get under the hood what is really happening. So we use this HCI method called think aloud. So we ask people to perform decision tasks, meanwhile try to verbalize their thinking process. Now we're trying to look at the transcript and see what is really going on. And then we conducted this study using two tasks. One is still this guess income group, it's a tabular data. And we added another task, which is looking at someone's bio and try to guess what's their profession. So this is a text data. We also want to do this study because we want to look beyond this kind of feature importance explanation. We want to explore example-based explanation. There are many different approaches to define, generate example-based explanation. We eventually opt for something very simple. We show people similar example and what are the AI's prediction and what is the ground truth. And this decision of showing ground truth turns to be very important. When we look at the data, right, people's decision outcomes, so we conduct experiment. In one condition, we have people make their own decision, and we show this kind of AI. And one condition, they have the example-based, one condition, they have the feature-based. So looking at the results, again, we find that feature importance explanation leads to over-reliance. And that leads to this human AI joint performance, not better than AI or human alone. In contrast, we find that example-based explanation leads to this complementary performance, that is, human AI joint decision is better than human or AI alone. You'll be surprised that it's actually quite a rare finding in this kind of empirical study of decision-making. And one of the reasons is example-based explanation did not reduce accuracy for cases when the model was wrong, but increased it when the model is correct. So importantly, we want to understand what is really going on in this quality process. Because we're interested in this question of over-reliance, and the flip side is what are the ways people can override AI to have appropriate reliance? So we look at the think aloud data. We summarize there are three paths for people to override AI decision and have appropriate reliance. And we also want to contrast these two kinds of explanation to understand why feature importance doesn't work and example-based works better. And I will walk you through it. So the first path for people to override AI is if people have a strong intuition about the decision outcome, and that is different from the AI prediction, then they just disagree with AI. But it turns out when people are given feature-based explanation, they're much more likely admit they actually don't know the answer. The reason is because this kind of explanation turns out to be disruptive to people's natural intuition process because they are visually overwhelming, they're overlaid on the instance itself. In contrast with example-based explanation, people can have the agency to just focus on the instance itself before attending to the example, so that they have a opportunity to form their own intuition. Then when we look at a second path, there's also a problem, is that we find that, so the second path is that people can reason about explanation and detect negative evidence so that they can reject the model prediction. But it turns out it's actually difficult for people to reason about the feature importance and detect model error. The main reason is because people's intuition about the feature is qualitative, right? Looking at this example, you may know certain keywords matter, but it's actually hard for you to say this keywords should be two shades darker or 2 degrees more important than the other. And when they're confronted with this precisely quantified feature importance, people are more likely to feel confused, and many of them choose to defer to the AI. We don't have that kind of problem for example-based explanation. And there's an additional benefit is examples help people form new intuition by inductive reasoning. People look at the example and realize, okay, professors tend to mention this kind of journal. So that is a new intuition about this journal is associated being with a professor. So that helps people to have this second path. The third path is also people try to recognize their limitation in the decision itself. So it turns out, for example-based explanation, this kind of signal is quite obvious. It's when the AI is making mistake for the similar example. So this kind of signal turns out to be highly correlated with whether the model is actually wrong. And they're also very salient. People really gravitate. This is the first thing they usually check. Meanwhile, for feature importance, in theory, there is a signal that is if the feature importance is not a significantly trending in one direction, it's an ambivalent decision, but only very, very few participants ever notice that. So I hope this study demonstrates that this kind of feature importance explanation, despite being very popular, they can have this multiple kinds of incompatibility with people's cognitive process. There's also an important lesson is that we should not take explanation approach as good for granted. We have to have careful empirical investigation. And to have explanation that are actually useful for people, they need to be compatible with people's cognitive process. One way is to do this kind of empirical study, understand what is really going on, and improve the technique and also design. And another path I want to talk about today is we can develop new explanation that are inspired by human communication behavior, so that we can more likely to have explanation that's similar to what people usually encounter, so that is more compatible with how they reason with explanation. So when we think about human explanation, right, the best paper to read about it, you probably are familiar with, is this Tim Miller's paper, right? He did a very excellent overview of social science literature, summarize what are some fundamental properties of human explanation. And today I'm going to focus on the bottom two, which are human explanations are selective and they're tailored to the recipient. What do I mean by that, right? Let's take an example that there's a car accident. Usually what leads to it, there can be dozens of event chain leading to it. And when you are explaining this accident, you are not going to talk about all of them. You are going to be selective. And social science literature shows that there are some common heuristic people follow to be selective. And which one you use also depends on your selectivity goal. For example, if someone is just interested in this particular observation that the damage seems to be surprising, and you're going to pick course that's most relevant to that, which is the speed is very high. If you're working with a police who is trying to diagnose the courses, you are more likely to pick something that's most abnormal, most unexpected. For example, the car made a sudden lane change. If you're trying to teach your children, don't make this kind of mistake, you're going to focus on courses that really should not have happened and can be changed with intention. For example, because the driver was drunk. So we're interested in mimic this kind of a selective property of human explanation. So we have this work that's published at accepted to CSW conference. This is a collaboration with Chen Hao Tan's lab at University of Chicago. The lead authors are Vivian Lan, Yimin Zhang, and Cha Chen. So we propose a framework to augment feature-based explanation so that it can be applied to any kind of feature importance explanation. But instead of showing you the raw output with all the different features, we want to be selective. We are going to select the most relevant, abnormal, or changeable feature to you. But how do we get there? Right? The idea is we want to learn about the recipient, the user's belief of what feature is relevant, abnormal, changeable, by having their input, having their annotation on a small sample. And in this work, we basically propose a design framework to think about what are the different input we can elicit and how do we present a selective explanation. But I'm going to walk you through an instantiation, right? Consider we have this ML system that to doing sentiment prediction, sentiment analysis, that's telling you this movie review is considered as to be positive, and it highlights the important keywords that you think the model think is associated with positive movie review. So this is this kind of original explanation from any kind of feature importance algorithm. The problem is it's still visually overwhelming. There are lots of highlights. And also you can get hung up on some relatively trivial disagreement, like why is Western relevant, the word Western relevant to sentiment analysis? So we want to learn your belief about what kind of words is relevant to movie sentiment review. And we can get your, we can learn that from your input, your annotation on a small sample, say 10 example movie reviews. And our framework proposed that we can have two types of elicitation. One is we can do critique-based feedback. We showed you this example, the model's explanation, and you tell me which words you believe to be relevant or irrelevant. And we can also have open-ended feedback. We show you the example, you tell me which words you believe to be relevant. Then we collect that data. We train a belief prediction model. We just use some off-the-shelf solution that are able to predict your belief, which words is relevant in new and unseen instance. So once we have that, we use that to augment the output. We gray out gray out features that misalign with the prediction of your belief, what is irrelevant. So essentially, this kind of explanation tells you the model picked up those keywords, but there are some keywords you would think is irrelevant anyway. So let's just pay attention to the word pretty good. That's what the model picked up, and you will think this is relevant for sentiment analysis. Then we conducted a controlled experiment. We have one condition for people to use the original feature importance explanation and one condition for people to use this selective explanation. And our study find that there are several benefits selective explanation offer. One is that it improves people's subjective understanding because the explanation is sparser, it's clear, people feel like they understand it better. Interestingly, we observe people actually like the AI system better that way. The reason is because they now have an opportunity, they have a say to augment AI explanation, and they turn out they improve their subjective perception of the AI. Most interestingly, we also find compared to the original explanation, selective explanation actually improve decision performance and reduce over-reliance. Why is that? I want to show you an example, right? So here's an example where the model is making a mistake. So the ground truth is a positive sentiment and the AI's prediction is a negative. And if you look at the original explanation on the top, the reason is because the model picked up some quote unquote wrong keywords, such as thinking depriving, the word cheap is an indicator this is a negative review. But once the selective explanation comes in, those irrelevant words are grayed out. And what's left is the word great and is more aligned with the ground truth. Indeed, if we look at the selective explanation, right? The percentage of highlight is more aligned with the ground truth. And I want to highlight that here, this worked is because people are able to provide a reasonable intuition in this kind of sentiment analysis, so that once the selective explanation comes in, the highlights is more aligned with the ground truth. So there is a way for the explanation to better signal model errors. So instead of just looking at a prediction, if you now look at explanation, you're actually more likely to make the right decision. And I want to highlight here, this works also because the grayed out here is indeed that contrast between human intuition of task boundary, what human thinks is irrelevant for the task, and model decision boundary, what model thinks is relevant. So we're directly presenting you this kind of a possible contrast, which is why it's signaling the model error. Again, this works because in this use case that people are able to provide a reasonable intuition about a feature. It may work less well in situation people are not able to do that, but there is an opportunity for example, getting input from domain experts and use that to augment explanation. And I want to end my talk with maybe a deeper analysis in how humans actually explain, right? So this is a model of human explanation by Mel. So when human explain, we're actually having two fundamental processes. One process is we're trying to gather information that will be possible courses. And there's another process, which is this impression management, which is essentially we have all this information, how we communicate them. And because it's impression management, because you have certain communication goal, and that will determine how you select from the information, how you present the information. And we can argue that a lot of XAI technique these days, which only focusing on disclosing the model process, is only concerned with this information gathering process. And there's a huge opportunity here in this communication impression management process, which ideally require some kind of representation of what is the recipient's beliefs about the model, beliefs about the world, and also the communication goal. The kind of selective explanation we presented is just one example of this, and I'm hoping that demonstrate this effectiveness of explanation that focusing on this communication piece, and also some nuances in terms of how we operationalize human behavior and what kind of benefits they can bring. And with that, that's the end of my talk. Thanks for your attention, and I'm happy to take questions.
We have time for several questions, please.
Hello, thank you for your talk. It was very interesting. I really like how you are kind of focusing on the utility of our explanations at the end of the day. But I think there's one point I didn't entirely understand around the selective explanations. So perhaps a broad question, do you think that there's any tension between impression management and sort of faithfulness of our interpretations? And could our selective explanations at all be adding to confirmation bias when we, drastically reduce the amount of information we communicate? Is it still faithful to the model, and are the humans only happy because it's, we've changed our explanations to match what they want?
Yeah, that's a great question. Indeed, there is tension between whether it's selective explanation or communication and the faithfulness, right? My personal view is whether faithfulness matter and what kind of faithfulness gaps matter depending on the context, right? If you're thinking about, for example, a kind of use case where you are deploying model, you really have to get to specific feature and changing them. There maybe faithfulness matters more, but there's also a point that there are different kinds of faithfulness gaps, right? It's instead of being deceptive and showing you the wrong feature, the point here is we're going to use some visual cues to emphasize other kind of information more than the other. I think to have the benefit of having something that's intuitive to understand, especially considering decision support use case, there is a limited cognitive resource. So in that kind of case, we might need to kind of prioritize the benefit of better communication without necessarily deceiving. And there we can have a lot of decision into what is the right interface choices of presentation, and that is possible. Did I miss any parts of your question?
No, maybe if I think that helps a lot. I think just clarifying the experiment perhaps. So when you ask the user, you present, it's particularly when, you know, it's like flipping it's a model error. How do you incorporate their, you know, selection of this is the word that you should be paying attention to?
Yeah.
Is there any changing in the model training, or is it kind of felt like a presentation of like an alternative set of facts, you know, that is more compatible with what the human wants, but might not be what the model is doing?
Yes, that's a great question. So I hope the talk piqued your interest to read that paper. So in the paper, we have a more comprehensive framework discussing like who should be the one providing the input, what are the benefits, what are also the ethical consideration, right? I think indeed, like who provides the input and can this person provide the right input matters a lot. One possible view that we're proposing is we have to see it as a way of giving people the agency. Right, they have a way to provide their input, and that is we consider in this kind of use case that we're more giving people agency rather than putting some other people's view into practice. But indeed, there's a lot of question in terms of will people introduce certain biases? Like in this case, I mentioned it works because people are able to provide reasonable intuition in this kind of sentiment analysis. But you can imagine other case, people also bring their own biases, and confirmation biases is indeed a concern. Yeah.
Okay, thank you.
Thanks for the question.
Do we have any other questions from the room? Oh, here's another question. Do you have any pointers for computer vision researchers on how to better design AI explanations? So, you know, you can make them more explainable, more understandable, less overwhelming, and like encourage the slow thinking that you suggested?
Yeah, that's a great question. I think it's actively researched area in HCI. There's a lot of interesting work. I personally have written a paper on this topic of human-centered explainable AI where we give some overview of work in this area. But in general, I think my suggestion is we need to do it iteratively. Right, we have to do user study, understand where are the gaps in order to improve our design. We're talking about computer vision, but computer vision also serve many different applications, right? We have to kind of ground it in the particular application, particular stakeholder to understand what people really need. And in particular, for your question about how do we nudge people to have more system to thinking, to pay more attention. One paper that would be interesting to check out is the title is co-living enforcing function for explainable AI, something like that. But the general approach is we should consider slow people down. Right. We sometimes think a seamless design that people can use it without thinking is a kind of good experience. But a lot of times we actually want to put frictions in this user experience. This can be as simple as asking people to make a decision before they see the AI's explanation, or allow people to click something to see the information they want. So adding the friction can slow people down and hopefully nudge them to have a little deeper cognitive engagement.
Thank you. Do you have a question? Yeah, go ahead.
A very nice talk, Vera. Sort of extending on the idea of the decision boundary and the humans sort of take on some of those perhaps harder samples around the decision boundaries. I was wondering if you or others in the community are what's your take on this, where the current state of the art is about the attributes and not so much the decision boundary, but sort of perhaps the dimensions, and in general, are the decisions being made by the AI, or perhaps the weight is being put on some of the latent attributes or factors that humans really care about. So explanation, in my mind, really is sort of after the fact kind of thing, and you know which words are being highlighted and all that. And so it's the harder question, or maybe the next level question, is really were the factors considered, were the right factors considered, sort of going back to the previous talk, the right answer for the right reasons kind of theme. So any insights into that, or any good pointers that you may want us to look into, or where do you think the research is headed in that space?
Yeah, that's a great question. I think in HCI, people ask this question of human AI complementarity. What exactly is the human AI complementarity? I think one point of view is we need to also think broadly in terms of the types of capability, right? Not just in terms of what kind of knowledge people have, what kind of feature people know, right? For example, we've seen some work lately that basically like having AI doing prediction is not necessarily the best use case for AI. Instead, we can use AI to gather information, summarize information. That is probably more useful for this kind of a decision use case. So that is very much actively researched area. For example, Ken Hosting at CMU and Krzysztof at Harvard could probably be a good place to read about. And I think in general, we probably also should take a broader view in terms of cognition, human capability, to think about, rethink what is the right complementarity for what a human is doing in those tasks.
Yeah, thanks for that. Just, I guess, a follow-up, maybe AI for assistance and feature extraction, maybe perhaps the easier problem, but the decision-making, AI for decision-making is, in my opinion, the harder, part of the application of the AI, and that's where some of these factors become a lot more critical. But yeah, thanks.
Totally. Thanks for the question.
Okay, I think we're at time, so let's thank the speaker again. Thank you. That is an amazing talk. Yeah, so now we're going to move on into our second spotlight session. And I think both of these are online, right? Okay, so the first paper is by Pushkar Shukla, Sushil Bharti, and Matthew Turk. And it's called Kavli Using Image Associations to Produce Local Concept-Based Explanations.
Hi, I'm Pushkar Shukla, and today I'll be presenting our work Kavli using image associations to produce local concept-based explanations. This is joint work done with Sushil Bharti and Matthew Turk. Consider an image classification network. In the slide, we consider an image classifier where, given an input image, we want to predict whether the input image contains cows or not. In this work, we attempt to design a module that is able to provide local explanations that quantify the dependence of a decision made by an image classification system in terms of relevant human concepts. In this case, our focus is on developing a module that can analyze and understand the reasoning behind the classifier's decision regarding whether the presence of cows in the image is dependent on the fact that the background consists of grasslands. On a high level, our proposed approach can be broken down into 3 different research questions. The first question focuses on determining what parts of the image are significant for decision making. In this particular example, we would want to identify the portions of the image that are deemed most valuable by the classifier when making its determination that the image contains cows. Secondly, what parts of the image does the model associate most with the concept? Here, we want to identify parts of the image that the model deems most relevant or representative of grassland environments. Finally, once we are able to solve the 2 questions, we would want to measure the overlap between the 2. A higher degree of overlap between image regions associated with decision making and image regions that are strongly associated with the concept implies that the concept has played a significant role in the decision making process, thereby suggesting a stronger dependency of the decision on the concept. We use the term image associations to refer to the overlap between regions in the that are associated with the concept and regions that are associated with the decision. Motivated by our intuition, we propose Kavli that combines 2 popular yet orthogonal image explainability techniques, TCAM and AI. Given an input image, we divide the image into superpixels and create k different images by randomly turning off some of the superpixels in the image. These images are then passed through the image classifier. To analyze the output vectors for a set of k images, a linear regression model is employed. These outputs are combined by binary vectors that indicate the activation or deactivation of patches in each of the k images. By incorporating these binary vectors as additional input variables, the linear regression model aims to establish the relationship between the output vectors and patterns of patch activation across the k images. The approach is similar to the line framework and results in a decision heat map, indicating what superpixels are most useful for decision making. The second part of our problem focuses on understanding what parts of the image are most associated with a given concept. To solve this part, we train a TCAP with the same frozen backbone as the image classifier, but a different classification head to model a given concept. We then follow a procedure similar to step 1, where all the k images are passed through the TCAP module and the conceptual sensitivities are fit into a linear regression model. This can be thought of as applying line over the output of the TCAP model. This results in a concept heat map that assigns weights to different patches in the image depending on whether these patches are linked to the concept or not. Now, to solve the third part of the problem, we measure the overlap between the concept heat map and the decision heat map. We do this by proposing a concept dependency score that is the product of the conceptual sensitivity of the model and the correlation between the weights associated with the concept heat map and the decision heat map. The concept dependency score tells us about the dependence of a decision on a given concept. A higher value of CDS score indicates a greater dependence and vice versa. Here are some results. We select images from this class zebra in the ImageNet dataset and evaluate the average concept dependency score for 4 different concepts: stripes, grasslands, indoor, and horse on the InceptionNet module. Our results show that the concept stripe has the highest CDS scores, whereas indoor backgrounds show the lowest CDS score. In addition to the previous analysis, we further conduct experiments involving different classification models, specifically focused on the zebra class. These experiments aim to evaluate and compare the performance of various classification models in accurately identifying zebras. Furthermore, we also conduct experiments for the basketball class, specifically targeting the concepts of ball, jersey, gender, and race. We also conduct experiments on the Selective dataset. Here, we evaluate a smile classifier trained on the Selective dataset. We calculate the the average CDS score for the attribute gender. The results show that the average CDS scores for females when they are smiling is much higher than all other class concept categories, implying that the model tends to associate the concept of female with the class smiling more frequently, even though there may not be a meaningful relationship between the two attributes. Our framework allows us to visualize the respective image associations by looking at the concept heat maps and decision heat maps to observe the commonality between regions useful for decision making and regions associated with a given concept. This allows the user to better reason about decisions and their concept dependence. To summarize our contribution, we propose a novel framework that combines two previously existing approaches to generate local concept-based explanations. Our approach attempts to measure the dependence of a decision made by an image classification system on a human-defined concept by utilizing image associations to provide explanations. Our framework also provides quantitative measures in terms of a CDS score and visual heat maps to explain the dependence of a decision for concept. In the future, we plan to extend our work in different ways. We would like to understand the effect of using pixel-based weight assignment techniques over patch-based weight assignment techniques. Also replacing attribution-based methods by attention-based mechanisms. In the longer term, we are also interested in the use case of association-based explainability methods like Kavli, and would want to compare them to other styles of explainability methods like attention-based approaches or concept-based approaches. I would like to thank you for attending this talk. Do check out our paper and poster and feel free to contact. Hi, we consider.
Okay. All right. I think we have Pushkar here with us, or like on Zoom. So I think there are a couple of questions in the chat that I'm first going to read out. One question is, how computationally expensive is it to compute a CDS score for each of the concepts using the line-based method?
So we do agree with it, like with the fact that it's very computationally expensive, and that is one of the major drawbacks of this model. And we are currently working on building techniques, and this is a work in progress to reduce the computational cost of the whole algorithm. It's slightly more expensive than the original line-based, like simple line approach and like calculating TK.
Okay. Also, we have another question. Can you explain how to interpret the CDS scores? So for example, in the SMILE classifier, the scores were like less than 0.1, but then for the zebras and stuff, it was like much higher.
Yeah, so the CDS score is model dependent. So for different models, the values are different, but it's similar to a correlation score where it's between -1 and +1. And like lower values mean like values closer to -1 means that there is a negative correlation between the attribute and the decision, whereas values closer to 1 mean there's a higher dependence. But at the same time, it's for each, like it's calculated per decision on a specific model. So different models might have different results. I hope that answers different set of scores. I hope that answers the question.
Yeah, thank you so much. All right, I think we're going to move on to the next talk. So this is also virtual, so I'm just going to start playing it.
Hello, my name is Caitlin Morrison, and I'm starting my third year as a PhD student in the Human-Computer Interaction Institute at Carnegie Mellon University. Today, I'd like to talk about a recent small empirical study that we did, which seeks to understand the alignment between human perception, vision architectures, and saliency map techniques. I'll present how there is shared interest among these three factors sometimes, and wrap up with some key takeaways from our findings. Even though saliency maps were designed to provide insight into the model's prediction, there have been numerous studies now showing that they can be confusing and misleading to decision makers, hurting the human AI team performance. With studies showing saliency maps to be misleading or confusing, several follow-up studies explored ways to design more human-centered saliency maps by trying to understand human perception. Past work has used a variety of approaches to understand how saliency maps align with human perception, including but not limited to eye tracking studies, image annotation studies, and rating the relevancy of the saliency map. Within the image annotation studies, there have been a variety of evaluations, such as comparing a single technique across multiple models. For example, one study investigates GradCam using the Saliency benchmark dataset, which includes human attention maps. This study looks at an EfficientNet, a ResNet, and a VGG. And since GradCam is an attribution method producing a heat map, they were able to calculate the intersection of a union between human attention maps and the saliency maps for GradCam from each model. Another study proposed a new saliency map technique, XAI, and visually compared it to GradCam for two different CNNs. Their visual analysis was to showcase simply how the XAI technique and GradCam capture different regions of the image. So while studies in the past have evaluated one architecture with multiple saliency map techniques, or multiple models of the same type of architecture with one saliency map technique, none of them, to our knowledge, evaluate different types of architectures with multiple saliency map techniques and compare them to human perception. Another dimension of debate related to human-centered explanations is which architectures aligns more with human perception. With vision transformer architectures becoming better than traditional CNNs in many cases, recent studies have started investigating which architecture should be used for high-stakes computer vision tasks, such as identifying species of butterflies to classifying plant diseases and diseases from manifold images. But before we can decide if everyone should switch to transformers or what saliency map technique they should use, we need to better understand the shared interests across these different dimensions: the explanation technique, the architecture, and a combination of both. More specifically, we seek to understand which saliency map technique aligns more with human perception, which architecture aligns more with human perception, and to what extent the saliency techniques and architecture choice play a role in how much shared interest there is with human perception. For our empirical study, we evaluated 2 attention-based architectures and 2 CNN-based architectures. All of the models that we used were pre-trained on ImageNet. We evaluated these models on a subset of ImageNet models from the ML interpretability benchmark. And this benchmark selected 20 classes from ImageNet and 5 images from each class, totaling 100 images. For every model, for every image, we generated the saliency maps with 2 different saliency map techniques. We compared the generated saliency maps with the attention maps from the ML interpretability benchmark, which were obtained from crowdsourcing studies on Mechanical Turk. Lastly, we compared the saliency maps to the human attention maps using the shared interest metrics, which were proposed by Bogus et al. In 2022. And those metrics specifically include intersectional union, saliency coverage, and ground truth coverage. The specific attention-based architectures we chose to use include the small twin transformer from Microsoft and a small class attention for image transformers model from Meta. These 2 models have approximately the same number of trainable parameters and approximately the same top 1 accuracy. For the convolutional neural networks, we chose to use an EfficientNet V6 and a ResNet 101 because they are similar in terms of the number of trainable parameters to the attention-based architectures that we use. Although we do have slightly less trainable parameters, we still consider this to be reasonable for comparison. Lastly, we chose to only evaluate GradCam and XAI as the 2 saliency map techniques. We chose these 2 because GradCam is very popular. It's canonical saliency map technique right now, and XAI is a more recent novel technique that is an attribution method like GradCam. The XAI authors also compared their own method XAI to GradCam for 2 different types of CNNs, which validates our own comparison here. In terms of our results, first we look at the shared interest with the saliency techniques as if we ignore the architecture, which means we combine the intersection over union for all architectures and only filtered by saliency technique. Looking specifically at the intersection over union metric on the y-axis and the type of saliency technique on the x-axis, we see that the mean for GradCam is statistically significantly higher than XREI. And this trend holds for the saliency coverage and ground truth coverage metrics. If we look at architecture and ignore that there are different saliency map techniques, which means we include the intersection over union for both techniques for each model, then we can see that generally the CNNs are more aligned with human perception than the attention-based architectures. However, the class attention for image transformers model is the only model that was statistically significantly different from the other three models. The spoon transformer was not significantly different from the CNNs. This trend holds for the other two metrics, the ground truth coverage and the saliency coverage. Lastly, if we look at all the shared interest metrics for each model and the saliency technique combination, then we observe that the shared interest metrics for spoon transformer and GradCam combination is statistically significantly better than the other models when paired with GradCam. However, for XREI, the efficient net is statistically significantly better than the other models when paired with XREI. These findings show us that saliency map techniques have shared interest with human perception sometimes. This motivates that it is important to consider shared interest sometimes as we continue to evaluate and understand how saliency maps align with human perception. These findings also show that choosing a saliency map technique and model combination is not trivial. We should avoid evaluating the model or the saliency technique in isolation when it comes to trying to choose which aligns the most with human perception. However, isolated studies like this could allow technical researchers to identify individual components of saliency maps or architectures that contribute to shared interest. Thank you to the workshop organizers for putting together this awesome workshop, to all the other presenters on their great work, and to everyone involved in reviewing our work. I'm happy to take any questions you may have now.
Okay.
Hello, Mike.
All right. I think we have Caitlin here with us on Zoom. So if anyone has any questions, you can step up to the mic or post it in the chat.
Hi there. Thanks so much. So a kind of meta question relating the saliency maps to human attention. Are you pretty much agnostic about whether that matters, or in some cases it does and in some cases it doesn't, in the sense that the machine is orthogonal to humans and the combination is better, or is there some sense that it's better to align the two, the human kind of axis and the machine axis? I'd love to hear comments about that.
Sure, yeah.
Open-ended question for you, yeah.
Thank you for your question. Yeah, I think when it comes to at least high-stakes decision-making, like Vera's talk earlier, aligning the saliency maps with human perception can be more ideal when it comes to human AI complementarity. So just because it will help them better understand the explanation and where the decision was coming from. But if it is not aligned with human perception, then perhaps the explanation, the saliency map may be identifying things that are not like relevant to the domain. So for clinical or for radiology, it may be highlighting things that were relevant to the model, but not necessarily relevant to clinicians trusting the decision. So I'm not sure if that answers your question or not, but.
No, that was great. Thanks so much.
Thank you.
Okay. Yeah, I actually have a question. What do you think makes, GradCam more aligned with humans than XREI? Like, what about the mechanism itself?
Yeah, that's a really great question. And I think at least when you combine it with the Swin, when you look at it for the Swin transformer, I think this is more attributed to the model itself than the technique GradChem. But if you ignore the model, comparing GradChem to XRI, I'm not actually quite sure. I don't have too many thoughts on what about the algorithm is making it more aligned with human perception. I mean, I've looked into it, but I haven't been able to determine it. So I think future work should really explore what is going on behind the scenes that is making it more aligned with human perception. But that's a really good question.
That makes a lot of sense. Thank you so much. All right. Let's thank the speaker again. And I am going to stop sharing because the last spotlight is in person.
All right. Thank you. Then I'm going to start with this talk, which is about patch-based intuitive, intuitive prototypes for interpretable image classification. I am Maaike Nauta, or actually I should say Dr. Maaike Nauta, because I achieved my PhD in 5 weeks. Thank you. And now I'm going to present this work. So if we have an image and it is classified by neural network as a certain bird, for example, we want to know, okay, why is it classified as this type of bird? So what is often done is that you have a model which is already trained, and then you later apply an explanation method like a heat map to get some insight about what the model is doing, but it doesn't give you the full insight of what the model is doing. So instead, I argue for models where the part where it explains reasoning is already built into the model. And we do that with these kind of learned part prototypes. So the model that we have developed is actually a sparse intuitive sheet that learns these kind of visual parts. So if you then eventually have an image, you can simply explain it by that it has found some of these parts. These parts have a certain importance to a class, and by basically just taking the sum of the relevance of these parts, you then have explained why the model has classified it. And the model is actually using this reasoning as a classifier. So the explanation method is the same as the model which is classifying the image. So actually a bit of the same as this game where you have to ask questions about some visual parts to eventually get to the answer about what type of images it is. And we developed this model by actually going back a step and deciding, okay, before we are going to start building a model, what are actually the things that we want the model to have in order to be completely explainable. And the first thing is that the reasoning should actually be understandable. So instead of having just an image with pixels, we want to learn interpretable features that are actually understandable and meaningful to humans. Then second, the explanation should be relatively small. You don't want to show too many learned concepts, because then the user doesn't understand it anymore. And lastly, the model should also be able to say, well, I haven't seen this before. Because if I give an image of myself, I don't want to be classified as a bird. Instead, I want the model to say, well, this is not a bird. I don't know what it is. And that is making it way more understandable for users and way more clear. So let's start with this first point, that the reasoning should actually learn meaningful features. That's actually quite different to what other works already did, because the issue with many of these works is that they learn prototypes for a certain class. But suppose that we have this data set with two classes. One is there is a son or a dog on the image, and the other is that there is not a son or a dog on the image. What existing models do is that they learn certain parts for a class. But if you have multiple reasons why it can be a certain class, then you will see that there's one prototype that actually is representing multiple concepts. It's both a son and a dog in one. And that's, of course, not understandable for humans. So instead, what we do is that we have developed a new method of learning, such that the dog is actually one separate prototype and that the sun is one prototype. And it also shows that just looking at the size of the model, so how many prototypes the model has learned, is not good to evaluate how well the model is, because this is just one prototype, but we have two. But of course, this is easier to understand than the single one. So how do we then learn these parts, these prototypes? We use simply we have a model, a convolutional neural network, because in there you can basically say that the latent space preserves information. So this location here roughly corresponds with the information in the image here. Then we can extract these in order to eventually learn the parts. And what's important here is that we actually have now this entangled the latent space. So every feature map is actually a heap map for one learned part, for one. And then, so this feature, the blue feature map here corresponds to one part. And important here is that, in other words, a prototype is just one value that is learned. In our case, it's just one node that is activated. So either a prototype is present, it's one, or a prototype is not present. It is simply not there. And eventually, we can then simply visualize the prototypes as the part of the image where it is found. So how do we then learn these prototypes? Well, we have made two losses. So we give two views of the same image, and we actually enforce the model to give eventually the same values here for those two views. So we say, okay, the prototype that you find in one view of the image should be the same as the prototype as you find in the other one view of the image. Of course, an easy solution would still be to simply give the same values here for all the images and all the image patches. So to prevent that, we added one extra loss term that forces the model to use actually the whole space of prototypes. So in one batch, all the prototypes should be present at least once. And although we have labels for our images, we are actually first only using this part. So we are at the first stage not using any of the class labels, and we're just learning the model what is actually similar looking for a human and what is not. So these are some examples of the prototype that the model learned just by using these two losses. And so each row is one prototype, and you can already see that, well, it's actually learning things that we as a human can also understand. And we haven't used here any labels of the classes. And in the second part, we do want the prototypes to be fine-tuned further so that we know that they are actually useful for certain classes. And we want to learn this last layer. So which prototypes are actually useful for which classes. And we used here a special function that I developed in order to make sure that this layer is sparse, because we don't want that all prototypes are used for all classes. We just want a few prototypes for each class. And then eventually, this is basically the reasoning that you get. So the model has learned the prototypes. You look where the prototypes are found, and you simply add all the scores. And the image is classified as the class where the score is the highest. So this is also globally interpretable, because you can see the prototype for all the classes that the model has learned. And it's also locally interpretable by just showing the prototypes found at just one single image. And the advantage of that is simply a sparse scoring sheet is that it can also handle different types of images. So even though it is trained on single object images, if you would add one extra cat, the model can still handle it, because it will find prototype for the one class and it will find prototype for other classes. If you have different classes all of a sudden in your image, then the model will look for parts, but there are actually no relevant bird parts there. So the scores will actually just stay low. And therefore the model is then saying, this is not a bird. And here you see some more examples of where you can have multiple animals in one picture, or you can have completely objects which are not related, and then the model will just give scores close to 0. And we can then see that, well, the accuracy is actually the same or higher than other methods that were already out there, but the size of the model is way lower. So the number of parts, the prototypes that it learns, is way lower because of this layer that we have in the end, which is really, really sparse. But more important is, okay, how good are these learned parts actually? Because as I showed in the beginning with the example of the sun and the dog, only looking at the number of prototypes is not giving all the information. So we also used from the birds data set, they had labels for each part. So we didn't use those part labels during training, but we could use it here to evaluate how good our prototypes actually were. And it turned out that you could evaluate how pure one prototype is by looking, okay, are all the image patches of one prototype, is this always of a single part, or are there maybe multiple parts merged? And the purity of our models was really high, showing that it is indeed learning parts which are, yeah, for humans also interesting and have a meaning. Then in some later work, which is actually not in the CVPR paper, but I thought let's add it here, is that we also added, applied it to other types of images. So here we have a medical image, and there we actually, it also learned these kind of parts to show what is relevant for a fracture and what is not. And even though we only had image level labels, so is there either these two nodes, it turned out that the model has actually learned types of fractures that that humans are also using. So even though we didn't give this information, we could map those part prototypes to the types of fractures that that human doctors are using. So you can imagine that then in hospital, you can either justify one image, so why did the model give this explanation, by showing that there was one single part found and that was therefore classified as a certain class. You could also validate the model to check, is it right for the right reasons? So for example, now the model could find these kind of tags indicating whether the image was of a left angle or a right angle. Well, this is apparently very interesting for one class, but you don't want the model to use its prototype. So you simply disable the prototype and you have fixed this bias. So instead of fixing biases in a data set, what is normally done with these kind of models, you can actually fix the model in the model, which makes it way easier to find these kind of biases and then also fix the reasoning. And it could even be that we find part prototypes that human doctors didn't know were useful, but maybe they are actually useful. So by having this explainability in the model, we can also learn maybe from the model. So that's also my view that I have for a responsible AI. So what we usually do, which is relatively simple, is we just have raw data, we put it through a model and we get a certain classification out there. But that's the easy way, but I think that there are other ways possible. So I say instead of doing that, let's go from raw data and I still use like a deep neural network or any other strong model, but then to learn features which we can actually, which do have meaning, which we can understand, and then use that into a model that a user can actually understand. So in this case, we have our features are these learned parts, and then a user can check the reasoning into a model which is understandable, like in our case, just that you have a sheet with scores, and then the user can check the reasoning of the model, and if it finds reasonings that it doesn't want, it can change this reasoning into the model here, and only then we will use the model for the final task. And then just as a bonus, in case you didn't know yet, we also have this webpage out there where we have classified hundreds of explainable AI papers with what type of explanation they are producing, what type of data they are using, etc. So this is already from a bit of an older paper, but in case you didn't know the website, then please check. That was it for now. I'm happy to answer any questions.
How do you fix the number of prototypes?
That's a good question. So we fixed the number of prototypes at the start because let's go back to the architecture. Let's go here. So here, of course, you have to link the number of prototypes eventually to classes. So we fix the prototype first, and if you have convolutional neural network that is given some kind of number of feature maps D, then we set the number of prototypes equal to D. So the maximum number of prototypes the model can use is D, but then later we learn a sparse scoring sheet, and it turns out that most of the prototypes are actually not needed. So in the medical case where you only have two classes, you don't need all those prototypes. So most of the prototypes, the weights to the prototypes of classes are actually then just not used because it's sparse. So the eventual number of prototypes is not set, but is basically really depending on your use case and the data set. So for the medical data set, eventually a number of prototypes, I think, was 14, so very low. So you set the maximum number of prototypes, and then the model learns what the least number is to still get a good to get a good data classification accuracy and get a low number of prototypes, while not having these issues with the sun and the dark being merged into one.
And the prototype is agnostic to the label, you said, so it's a kind of self-supervised.
Yeah, so in the first stage, it is to make sure that the model learns, okay, what is for human looking similar and not. And then in the second stage, we are using classification labels, and then the model can still change the prototypes a little bit to make sure that they are actually useful for the final task.
So in the second fine tuning, you still are updating the
yes.
prototype according to the label.
Yes, but the learning rate is then way lower than in the first stage, to prevent that the model will then still merge the sun and the dark into one. So we first have the first phase to make sure that it really sees that as different concepts, and then later you can just make sure that the prototype are a little changed to be useful for the task, but still keep this this concept that a human would say that prototypes are visually the same.
Follow-up, like how many prototypes, what layers, like you have CNN, a bunch of layers, different levels of abstraction in there. Do you just decide which layers to pull your prototypes out of, or do you pull them out of all of them? And then
we basically use the last layer. So this architecture is actually quite similar to a normal CNN layer. So you also just first have these features map, and then you add one extra layer to if you have certain classes to get to the classes. So we basically have that same architecture, but then we are not using this linear layer for the classes, but we are using this linear layer to learn parts that are interpretable.
So stuck on the end of the feature.
Exactly.
Basically.
Yeah, exactly.
So that any network that spits out a feature vector, you would put this after the feature vector.
In principle, yes. The only restriction is that we assume that the location in the feature map should be just the same as in input image. But if you have a convolutional neural network, that is always the case. So then you can use any convolutional neural network indeed.
Okay. Sorry, I think we're at time, so maybe we can continue the questions in the poster session.
Yeah, exactly. So I have a poster session now. I hope that my poster is there, because I'm also at the main CVPR, and you could only get the posters that are presented tomorrow. So I hope my poster is now already there. If not, then I will also have my poster tomorrow morning.
All right, so now we're going to head downstairs to the second poster session. So they are in person at the West Exhibition Hall, locations 203 to 241. So basically where it was today morning. And we're also going to be playing the 2-minute videos for the authors who couldn't attend in person. And please do come back at 4 for Dr. David Bao's talk. This one.
Hello, my name is Steve.
Hi, David. We will introduce you in a couple of minutes. Right.
Sounds good.
Hi, everyone. We're going to get started in about 2 minutes, waiting for people to trickle back from the poster session. Great. So we'll get started with our last two talks for the session. Thank you all for sticking with us for the whole day. We know it's been a long day, but we've really enjoyed seeing so many of you. It's my great pleasure to introduce Dr. David Bao, who's an assistant professor at the Northeastern University, Corey College of Computer Science. He received his PhD from MIT and his bachelor's from Harvard. And previously, he worked at Google and Microsoft. We did our PhDs at the same time, so it's a great pleasure to introduce Dr. David Bao. And at the time, he was known for some work on network dissection that I'm sure many of us had heard about, which really studied individual neurons in deep neural networks. And since then, he's published a number of works on the interpretable structure of learned computations in large models in vision, as well as in language. Also having kind of had the wisdom of coming back as a PhD student in kind of a second career, in his first career, he was also co-author of a textbook called Numerical Linear Algebra. Dr. David Bao will be giving a talk on causal explanations for us today.
Great. Am I live? So,
yes.
Okay, that's
and you can
that's
share
great.
your screen now.
Oh, let me do that. Okay, so let me. I'll see if I can pop open my slide deck, and then figure out which window to share here, and then we'll get going. PowerPoint over here. Okay, is that live? Great. So I don't have a view of the camera of the room.
Wait
but-
1 second, David. The screen share hasn't gone through yet.
Oh, it hasn't gone through. Okay.
Maybe try it again.
Oh, okay. It says my screen sharing is paused for some reason. There's a, if I say resume share,
yeah.
It looks like this is there's some moderator control here. I've actually never experienced this before on Zoom. There's a little orange thing that says my screen sharing is paused. I'm going to stop sharing and I'm going to try sharing again. Okay. Yep, it's doing this for me again. Isn't that
Okay, give us
interesting?
1 moment.
Okay. Yeah. Well, but first of all, while I'm waiting for the screen share here, I just want to apologize for everybody for not being there in person. I'm actually sorely missing being able to see Vancouver. I'm sure it's very beautiful this time of year, and I'm hoping everybody's having a good time there. There's I have a lot of friends who are at CVPR, and I'm missing seeing all you in person, and it would have been great to see you all.
David, can you try sharing your screen one more time?
Yes, I'm going to do this here. Do you see anything? It says, oh, it still says paused here. Yes.
Let's try to stop the screen share and then let's see if we can request the screen share or something.
If in the very worst case, if we are totally stuck, I can send you a link to slides or something, and I can kind of narrate and ask people to go forward or whatever.
Windows, okay. All right, David, someone said in the chat, sometimes it will say paused if you have the window minimized.
If I have some window minimized. Okay, let's see. I don't have it minimized, but I'm going to try, let me see if I can put PowerPoint in a different mode. And maybe that'll help. Maybe that'll be easier or something. Okay, let's see here. Slideshow. Custom show. Let's see. Okay, I'm going to try sharing it a few different ways here. So I'm going to just share this whole desktop.
We got this. Yes.
Does that work better? Whoa, okay, yes. Something. Okay, great. Sorry about that. Some interesting technical issues. All right. So yeah, what am I going to talk about today? So basically, I have sort of 3 ideas on interpretability of big models, which I think were sort of the things that I think are important nowadays in interpretability work. So I thought I'll talk a little bit about some of the technical results in the last year and a half, and but mostly to try to tell these three stories. So one of the stories I think is this this transition that would be good to make, that I think that we're starting to make in interpretability research, from sort of understanding correlative interpretability to understanding like causal interpretability, and I'll give a couple examples of that. But I think that one of the things which maybe we've been pretty cautious about our approaches to interpretability, but maybe too cautious. I think that maybe it's a time for optimism, that maybe we can, maybe interpretability is possible. Maybe we can understand systems well enough that that we can really build, very predictive, very causal models of what's going on in these big black box systems. The second thing is another thing that I think is sort of a fallacy that's been around for a long time, which is that there's a trade-off between interpretability and performance. And I think that one of the things that maybe we should strive for is to find situations where interpretability actually aids performance, that if you understand more of what's going on, then the whole system, either the system together with a human, or maybe the way that we work with a system actually improves. And so I think that I think that that's not impossible. I'll talk a little bit about some examples there. And then the third thing is that I think that if we take these kind of ambitious goals as a benchmark, then I think it'll actually be helpful in making more community progress in interpretability research. Interpretability is really a community effort trying to build a better understanding of systems. And so so the third thing is sort of a call to action. And what I'm going to do is I'm going to show you a few pieces of research, and then I'm going to actually intentionally highlight places where the community has been working together to sort of improve our understanding of the same systems. And so so I'll talk a little bit about what I think is necessary for that. So okay, so but what I'm going to do is I have it looks like I just have maybe 20 minutes left because we spent a little time with Zoom getting things going. So I'm going to run through maybe 10 minutes on each piece of research that I want to talk about. I want to talk about two pieces of research and try to tell this story along the way. Okay, so the first piece of research is this Othello paper, and I don't know if you guys have seen it. Both my examples sort of come from outside the computer vision interpretability world, but I thought that the Othello paper was really interesting. So here's how this story of the Othello paper works. So if you've ever played the game of Othello, it's just a simple board game. It's played on an 8x8 board with black and white pieces that you can flip over according to some pretty simple tic-tac-toe-like rules. And so suppose that you had a great friend who liked to play Othello with you, and they're a very serious Othello player. They come over every weekend, and without uttering a word, your friend would sit down, and then you would take turns moving, and you'd play in a very formal way. You'd say, you'd call out the moves. You'd call your move D3, and then you play two piece, and then your friend would call out the move C5, and then they'd place their piece, and B6, E3, right? And until the game was over, and then you'd score it up, and then your friend would go home. And after many weeks of playing these games, you're sitting there pondering your move, and then suddenly you hear this bird from outside your window make a tweeting sound that sounds a lot like E3, which sure enough is a valid move. And so you call out E3, and then you hear then you're fascinated by this bird. You listen again, and the bird is actually calling out legal moves, and somehow has started to imitate the audio of your game. And so so you and your friend stunned by this, run outside, and sure enough, there is a bird outside the window making the sound, and you're wondering what's going on, how the bird is doing it, and then your friend notices, oh, there's this little arrangement of seeds that the bird has arranged on the ground in front of them, and the seeds look a lot like the arrangement of an Othello board. And then you think, oh well, that's it. That this bird has really learned how to play Othello. And so of course, the bird in this game is the language model that Kenneth Lee played with, and the seeds in front of the bird are an analysis of the language model's inner state. So let me tell you a little bit about the language model story of what Kenneth Lee did with the Othello game. So he basically trained a small transformer, sort of a toy transformer language model, to take these kind of inputs that you see on the left, D3, C5. There's only 60 valid moves that you can play in an Othello game. And then on the output side, the model would output what a valid next move is. So this is a classic sequence modeling task, pretty well understood, and he trained it to be able to achieve pretty much 100% accuracy. And so now, what does accuracy mean here? At any given moment in a game, there are multiple valid moves. So the ideal output for this transformer would basically be to say that each one of these moves is equally likely, and so without too much training, you can pretty quickly get a transformer that can get more than 99% accuracy. If you measure its ability to tell the difference between what's a valid move and what's not. Okay, so this is nice. So here's our little bird who knows how to call out valid moves. Now, what Kenneth did is he used sort of classic interpretability method. In natural language, they call it classifier probing. Here, in vision, sometimes we call it task, sort of task vectors. But what he did was he trained these small models to take a look as input one of the internal states of the transformer and answer the question: do we believe that the board state has a white piece or a black piece, or is a blank at a specific location? So there's a small model that tries to predict what is the state of the square F5. And there's 64 squares on the board, so he trained 64 models, one for each square, to try to figure out what was in that square. And it turns out that you can also train models that get this very accurately. And this is kind of an interesting surprise, right? Because you could imagine a lot of different ways for getting Othello to work. But one of them is to actually imagine the Othello board itself, but you might imagine that there could be other ways of just sort of pattern matching your way to getting the next sequence. But the interesting thing to see is that this model seems to have a set of internal states that correspond to spots on the board, and so Kenneth actually visualized these little classifiers that he created. They're small enough that you can create low dimensional embeddings of them. And so here's, in each one of these visualizations, each one of the points is one of the little classifiers, and we're basically visualizing the weights of the classifier. And you can see that they're arranging these beautiful shapes that sort of are reminiscent of taking an Othello board and draping it over a sphere, or sort of arranging the symmetry of an Othello board in an interesting way. And you can see that these classifiers are pretty accurate. Depending on the way that he trains them, he can get up to like 98% accuracy in being able to read out what the state of the board is by just looking at a hidden state. Which, okay, so this is great. So I'm sort of telling this story because it's a toy example of the type of interpretability work that a lot of us do, and because it's a toy example, you can get really clean results out. You can go look inside the network and you can ask, does the network contain knowledge of the F5 square? And when it does, you think, wow, that my network my network must think the way that humans do a little bit in this respect. You know, it's tracking the state of the board. But one of the problems with this this kind of conclusion is you're never sure if the network is actually using this information to make its decisions. The fact that it has the information isn't the same as it's using the information. So the first idea I want to sort of emphasize in the talk is this transition from prediction to causation. So the next experiment that Kenneth did after he found the equivalent of all the crow's seeds is he did the equivalent of running out to the backyard and noticing the crow's seeds and then moving the seeds around. So he changed the hidden states by fooling the classifier, you know, just by backpropagating through the classifier to change the hidden state. And when you do that, and then you let the transformer continue out of that intervened state, then it will change its predictions. And the thing that he found is that when you do that, it will actually change its predictions to follow the rules as if the board state was the way that you perturbed according to your view of the internal state, which is really interesting. This is really proof that not only does the model have this view of the world that you interpret, but that it's using it to accomplish its goals, to make its decisions. So I think that this is my first recommendation for us all, is to move from predictive interpretability to causal interpretability. I think it's really a pretty strong thing if we can do that. And there's definitely situations where we can achieve it. So and this is one. Okay, so the other interesting thing that you can do in this case, and I think I'd encourage you, if you ever do causal tests, is to do this experiment that that Kenneth did, which is, you know, of course, if there's two types of causal tests you can do. One is you can move the board into a state that would be a state as if somebody made a different move in the game, right? And then you can see, oh, well, if they made this other move, if they made this counterfactual move, then different other future moves would be illegal. The other thing that you can do is you could actually pose a counterfactual situation. You could actually move the state into a case that would have been impossible in a legal game. So when he changes the state in an impossible way, then he can kind of ask, well, even though this board would have never happened in a real Othello game, you could still apply the rules of Othello. Does this model really apply the rules even in impossible games? And he found that this transformer does indeed do that. So I think this is kind of the interesting promise of this type of explanation, is that you can potentially understand how these models are behaving when you push them way out of domain. So okay, so that's going to end up leading to my next story. So Othello is fine, all fine and good. Let's apply this to sort of a more real world situation. And so you may have seen the Rome paper. If you've not, then I'm going to give a quick overview of how that works here. And the idea is to use the same kind of ideas of the Othello thing, but on large language models that were trained on natural text. And so the thing about these large models is that if you have a sentence like the one that I'm showing you here on the left, Edmund Neupert performing on the, and here we're going to predict the next word, which is going to be grammatically correct. It's going to predict piano. You'll notice that a lot of times it's also semantically correct. Edmund Neupert really is an 18th century pianist. And so the model is correctly predicting that this person plays piano, which leads to this kind of question: can you extract other knowledge from these networks? And you know, it's not a big surprise in the age of ChatGPT. Of course you can. It knows that Miles Davis plays the trumpet, Jimi Hendrix plays the guitar. It seems to contain a little knowledge base. And so the equivalent of the seeds that we're going to go look for is we're going to ask, you know, where is this knowledge inside the network? And to do that, we're going to build a heat map inside the network of what parameters are the most relevant rather than what inputs are most relevant. And here's how we're going to do it. We're going to transplant data using interventions to identify the effects. So what we do is we run the network twice. The second time we run the network, we sort of poison it. So this network here up top is correctly predicting Miles Davis plays the trumpet. And then below what I've shown is running exactly the same network, but simulating a case where a bunch of noise is injected at the time that you mention Miles Davis, as if a big truck has rolled by. And now, unsurprisingly, the network can no longer correctly predict that Miles Davis plays the trumpet. It has a hard time understanding who you're talking about. And so this is a poison network. It can no longer, it's sort of our disease case. It can no longer perform the task correctly. And what we're going to do is we're going to try to find a little piece of medicine to cure the disease. Now, obviously, we could try to cure it by putting Miles Davis back here, and that would fix the problem. But we're going to try to see if we can find something more economical that reveals the mechanisms. And the way that we're going to do it is we're going to pay attention to the answer here while we change internals of the network. We will take a hidden state from the healthy run, and we will transplant it down to the disease run, and then we'll let the computation proceed. And then when we do that, then it'll affect the computation, but most of the time, when we do that, it doesn't actually sort of cure the disease. Most medicines don't work, right? So when we do this, and we just move down a random hidden state, most of the time the result remains corrupted. But once in a while, we'll bring down a hidden state, and the computation will propagate through, and then we'll get a change in the output, which leads it to the correct solution. And that sort of gives us evidence that whatever magical information was in this hidden vector here was part of the critical computation path that was necessary to do the magic of getting the right answer out, right? So let's show you what an experiment like that looks like. So this is some real data. I've made the sentence a little longer so you can kind of see where the white space is here. So Brian De Palma works in the area of film as the correct answer. And what I've shown you here is in white is all the different hidden states of the network, which if you tried to transplant them from a clean to a corrupted run, these have no effect. All the white things have no effect, but the dark ones are the ones that have an effect. And you can kind of see there's two regions which have an effect. There's a region down here which is really unsurprising. These are the states right before the model outputs the word film, and transplanting a state here from a network that's already ready to say film to a network that doesn't know what it's talking about, we'll just get it to regurgitate the word film. So it's not surprising at all that if you transplant things in this region of the network, sort of at the very, very last layers, that you can kind of cure the symptoms of the disease. But the interesting thing is that there are also a few states here really early in the network, which if you move them over, then they'll cure the disease. And it's so early in that thing, it leads you to the question, oh, is this the cause of the problem, right? What is going on in these states? So I'll just show you a few more examples. So, this is pretty systematic. You can kind of see these causal effects showing up early in the network in different situations. Here's a different type of noise. We have a sentence, Shaquille O'Neal plays the sport of basketball. And instead of injecting noise here, what we do is we corrupt it by bringing over a hidden vector from Megan Rapinoe's sentence. And you can see that you get this very, very sharp location here in the middle of the computation that if you move over a single hidden state anywhere in this region, then you can cause Shaquille O'Neal to play the sport of soccer instead of basketball. Okay, so there's a bunch of this causal stuff is great for decomposing things in different ways. We found that the causal effects were stronger if we used pieces of in these transformers. We have these different types of components. There's MLP components versus attention components, And if you move the MLP components over, you get much stronger effects at this early state, and they don't really make a difference at the late state. And if you move over attention components, you get very strong effects at the late location, but not really much at the early location. And so that sort of suggests that whatever's going on in this mysterious early state is something that's dominated by MLP, which led us to do a whole bunch of other analysis. I'm not going to go through all the details, but it leads to this sort of idea that the factual knowledge is, you know, we can kind of physically locate it. It's at the last subject token. It's a pretty sharp result. It's pretty clear it's in the MLPs. And then it's at some range of layers. You know, which layers it was, you can see in all these pictures I showed you that which layer it is a little bit fuzzy, but there's some range of layers where the knowledge seems to appear, right? And but then now that's a bunch of causal things, but you want to test this in a more causal way. And so to test it in a more causal way, we designed a way of editing the MLPs at those layers to see if we could actually change the network to have its knowledge, instead of, say, knowing that the Eiffel Tower is in Paris, knowing that the Eiffel Tower is in Rome instead. And so let me run through this a little bit. The upshot is you can kind of get this to work, and then the stunning thing is that not only can you get this to work, but when you do it and you scale it up, it actually performs better than the traditional fine-tuning methods that you would use to adjust a network based on small number of few-shot training examples. So here's just some performance curves. This is something that's even better than fine-tuning. This is a hyper-network method that's designed to be sample efficient, and using this interpretable method sort of improves things. There's another view of the performance graph. There's an interesting specificity generalization trade-off. Okay, so but the big message that I want to come out from this, and I don't know if I skipped over the slide here, is that interpretability can actually aid performance. In any other area of computer science, this would not be a surprise, right? Like if you understand a computer program better, you should be able to fix bugs better in a more, in a better way. For some reason, in our community, in our culture, in machine learning, we tend to believe that there's a trade-off between interpretability and performance, but I don't think this is actually true. I think that as we get to understand what's going on inside models better, we should be able to get better performance effects out of them. I urge us all to hold this up as a goal. If we have pretty high standards and we put causal effects as sort of our objective, I think it leads to a third benefit, which it enables community efforts. So what I'm going to do is I'm going to emphasize a couple interesting papers that showed up in the last year that I think were enabled by the fact that we have pretty clear causal benchmarks on the interpretability work that I showed you here. And so, for example, we showed that you can edit things pretty well, and that we believe that it taught us something about where knowledge is stored in the network. And Peter Hasse and B. Kim have this great paper that comes out later and says, well, using these sort of causal methods, we can question some of your conclusions and your interpretability results, which I think is great. I think a lot of previous interpretability work is sort of like, is it interpretable? Well, you see it when you know it, and a lot of it is very subjective. But I think that if you hold yourself up to the question of, are your interpretations the most economical explanation for some causal mechanism inside the network, then it leaves room for people to do things like publish a challenging paper that says, David, I think that you got it wrong. I think that you can do this editing at other layers besides the layer that you identified, which opens up more interpretability mysteries. But I think that it leads to progress. I think after the Peter Hasse paper, Jiva did.
Hi, David.
Yes.
Just wondering if you wrap up in 2 minutes, just so we can leave room for a few questions.
Oh, yes. Sorry. I'm almost at the end. I will give one last final example. And if I were there in person, then you would be able to tell me, oh, yes, David, you're running a little long. But I'm in the last minute or so. And so I just want to return to Othello. So one of the things I don't know if even if you read the Othello paper, you may not be aware of this, a few weeks after the Othello paper hit archive, one of the interpretability researchers out there, Neil Nanda, sent us a nice email saying, "Hey guys, I think you missed something." And the interesting thing that he pointed out was that these probes that we have don't seem to be capturing the right representation of the Othello state, because we trained these probes to predict whether an Othello state was a white or a black or an empty square. And he pointed out that if you train the probes with a parity goal to predict whether the square is owned by the player making the move or the opponent of the player, so that the probe would flip on each move, then the probes can be much smaller and simpler and linear, and they have better predictive effects that you can benchmark compared to the ones that we publish, which I think is, again, another great example of the community cooperating because we've got nice objective ways of measuring our own interpretability results. So I'll just leave it on this slide. The three takeaways: interpretability is possible. Really complete interpretability, I think, is possible. We're having more and more success at it. Interpretability and performance should not be a trade-off. We should aim to have interpretability that's good enough to aid performance. And then the third thing is that we should recognize that interpretability is difficult, but it's also a community effort, and we should be practicing the research in a way that allows each other to challenge and build upon each other's results. So that's my talk. I'm sorry I went a bit over. If I don't know if there's a time for a question or two.
Great. Thanks so much, David. We have time for one or two questions. If you're in the room, if you could come to the mic. If you're on Zoom, if you could just drop your question in chat.
Hi there. Thanks so much for this talk. I didn't know birds could do this. Hey, so my question is this method of probing and coming up with causal interpretability. Can you speak to how that might interact with the FDA? Because the FDA is trying to figure out how to deal with these models. Is this a scalable form of explanation, for example?
Is it a scalable form of explanation? Oh, so I think that I think we're still in a state, and so there's a few. I could sort of have done a talk on the big problems that are still facing us in interpretability, and maybe next year. The this whole framework that I've shown here is still sort of based on this model of where we hypothesize something that we think would be explainable, like an Othello board, or some relationship inside a model of like how we think the logic is done, and then I think that these methods are very good, and methods that are being developed now will be better at testing a hypothesized model of mechanisms against what's really going on in the model, and then giving us sort of causal correspondences and things like that if they exist. Is it scalable? It's not scalable in the traditional computer science sense, because these systems may have thousands, millions of different types of pieces of logic that they're providing, and here we're still depending on resourceful human beings hypothesizing these things to test. So that's one of the questions, is how to scale this type of thing. I think that there's a bunch of ideas on how you might be able to do it. Maybe you'll discover a way of doing it, but I wouldn't say that that's solved yet, the scalability question. Does that answer your question?
Yeah, it does. Thanks so much.
Mm-hmm. Yep.
Great, David. I think we're out of time, but thank you so much. Let's give David another round of applause.
Thanks, everybody. I really appreciate the chance to talk, and sorry I couldn't do it in person. All right.
Share or As we're transitioning, we're running maybe about 5 minutes late. I'll introduce our next speaker in a bit, but I just want to encourage you guys to stay at the end. We're going to give some very brief closing remarks, and we really want to hear from you guys what went well about the workshop and what we can improve for future iterations. So bear with us for a few extra minutes, and sorry for the technical delays. Is this being shared? Yes. You might need to request me to share, or this computer to share. Is this the right one? Yeah. Share the top. Click on it right now. It might need a request. Sorry. Sorry, just give us one more minute. All right. Does this work or no? This one or this one? I might be sharing the presentation version. All right. Swap displays or no. Or desktop too. Sorry. Sorry, guys. No problem. Yes, if you guys can all help me figure out where the swap button is. That one? Okay. Thank you, Allison. Great. Nothing like technical difficulties at a computer science conference. All right. So we're really pleased to introduce our last speaker, Dr. Alice Xiang. She's the global head of AI ethics at Sony, and as the vice president leading AI ethics initiatives across the Sony group, she manages the team responsible for conducting AI ethics assessments across Sony's business units and implementing Sony's AI ethics guidelines. In addition, as the lead research scientist for AI ethics at Sony AI, Dr. Xiang leads a lab of AI researchers working on cutting-edge research to enable the development of more responsible AI solutions. She also recently served as a general chair for the ACM FACT conference and on the leadership team of the Partnership on AI. Dr. Xiang is uniquely positioned to give this talk as she's both a lawyer and a statistician. She holds a JD from Yale Law School, a master's in developmental economics from Oxford, a master's in statistics from Harvard, and a bachelor's in economics from Harvard. Dr. Xiang will be giving a talk on being seen versus misseen, tensions between privacy and fairness in computer vision.
Hey, thank you all so much for sticking around until the end, and thanks so much to the organizers for the opportunity to present to you all. And apologies, I'm still getting over some upper respiratory stuff, so hence the mask and the slight difficulty in hearing me. Are you all able to hear through this mic and stuff? Okay, great, awesome. So today it's my pleasure to present to all of you being seen versus misseen, tensions between privacy and fairness in computer vision, which I published recently in the Harvard Journal of Law and Technology. This is a little bit different from the talks that you've seen today so far, in that it has more of a legal flavor and also is a bit more privacy and fairness oriented than explainability, but it is at its core about data availability, which is something that's very key, not only in privacy and fairness, but also for explainability and in terms of the types of explanations we can reasonably provide. Before I get into this talk, I wanted to provide a brief overview of our AI ethics research lab at Sony AI, since we're a relatively new lab. So basically, the goal of our lab is to work on developing solutions to enable AI ethics in practice. So what this means is we try to tackle fundamental unsolved problems that are preventing the implementation of more responsible AI practices, not only among Sony's business units, but also in terms of the academic research community and helping to inform industry best practices as well. Our team is new, but quite large and constantly growing. We're split across the US, EU, India, and Japan. So we have quite diverse representation on our team as well. And our focus is on these three areas. So ethical data collection, bias detection, and mitigation. And in particular, a lot of our work is in the computer vision domain. Just to provide you guys a few examples of that in terms of our more recent technical work. So we have this paper, which we presented recently in iClear, A View from Somewhere, Human-Centric Face Representations. And basically, the goal of this paper was to address the issue that oftentimes when you're working with large data sets in practice, they are going to lack sufficient labels to actually do fairness relevant work. So you're not going to have sensitive attribute data, for example, in order to test for diversity in your data sets or do fairness evaluations. And so what can we do in that context, given often the lack of labels and the limitations with the labels that we do have? So for this paper, we leveraged an odd one out face similarity metrics from human judgments to learn a continuous human interpretable face embedding space in order to assign diversity/similarity scores to unlabeled data sets. And so the goal of this basically is to enable folks to compare data sets where they don't have these labels, and they can say at least these faces are more similar versus less similar than faces in a different data set. Also, this enables us to avoid using stereotypical representations and some of the problems that we have with collecting these sorts of sensitive attributes. In addition, we have this paper upcoming in ICML that is called Men Also Do Laundry, multi-attribute bias amplification. And basically, this is in the image captioning context and tries to tackle the fact that a lot of the work in this space thus far has measured bias just along singular attributes. So you might have gender plus an object like computer, for example. But when we're thinking about the types of biases that we might see in the computer vision context, part of the challenge is just how rich image data is and how you have so many different object-subject co-occurrences. And so we propose a new metric that captures bias amplification not only among one attribute, but among multiple attributes. And we show that on average, bias amplification from multiple attributes is greater than from single attributes. And if you use bias mitigation techniques that focus exclusively on singular attributes, you might inadvertently end up amplifying multi-attribute bias amplification. That's just a very quick overview of a few of our other relevant papers, but for today, my primary focus will be on this one, which focuses on tensions between privacy and fairness when we try to implement more ethical AI practices. So just as a preliminary note, this paper is basically focused on human-centric computer vision, which I define here as computer vision systems that rely on images of humans for training and or testing. So this can be pose estimation applications, face body detection, face verification recognition, but it can also involve other sorts of use cases like object detection, where even though the focus is not necessarily just on human images, humans might be present in the images. And in addition, this is something that's not new to folks in this audience, but one thing I like to stress at the top of this is we're going to be talking a lot about regulatory incentives, and a lot of regulation in this space has been very focused on facial recognition technologies. One thing that's important to note for the purpose of today's talk, though, is there's not just HCCV for the purpose of facial recognition, but for a wide variety of other use cases, many of which are far lower risk. So we can think of HCCV for entertainment purposes, in robotics, in photography, everything as simple as autofocus in some cameras nowadays, and even automatic bokeh filters. So there's a wide variety of different use cases that we're talking about here. So if we look at what's happening in the regulatory space at the moment for folks who are working on HCCV, we see a few different types of approaches. So first off, when it comes to particularly high-risk use cases, such as facial recognition for law enforcement, there has been a movement towards prohibiting these particular use cases. So this has included on the US side, a variety of state and local moratoria on these technologies being used for those purposes. And also in the EU AI Act, there are prohibitions on the use of real-time remote biometric identification by law enforcement in public spaces. There's also an approach in the EU AI Act of imposing high-risk requirements on certain types of HCCV technologies. So, for example, more expansively, remote biometric identification systems, not simply those used for law enforcement, but these technologies in general would be subject to high-risk requirements. And then broader than that is biometric information privacy laws, and that's a major topic for today's discussion. And this encompasses laws like GDPR in the EU, but also many state biometric information privacy laws in the US. And these are notable in that they were designed before HCCV became as prevalent as it is today. Many of these laws came on the scene in like around the 2008 time period. And this is interesting because even though they were not necessarily designed for these types of technologies, they have very significant implications because they regulate the extent to which biometric information can be processed with or without the consent of the individuals. And generally speaking, HCCV technologies always involve this type of processing because something as simple as just measuring the distance between the eyes counts as biometric processing under certain laws. And so what we're seeing in terms of HCCV is a growing awareness around both these privacy concerns and also these fairness concerns. So there's been an increase in lawsuits around the privacy considerations of people's biometric information being processed by various biases in the system. So, this image over here is a paper discussing some of the biases in pedestrian detection systems, for example, and them working better for light-skinned versus dark-skinned individuals. So given that we want to optimize for both of these areas and not sacrifice one for the other, it's worth considering how do we approach possible tensions between these. So just to illustrate, what I mean by tensions in this space, one example that I find instructive here is the diversity in faces dataset that IBM released in 2019. So this data set had a very positive motivation in that the researchers wanted to provide a more diverse and balanced face image data set for researchers to use, not only for fairness purposes, but just generally to use in contexts where you would need diversity and balance. Now, the problems with this data set, however, were that like many computer vision data sets involving humans, it used flicker images that thus did not have the explicit informed consent of the people in the images. And so this led to a lot of lawsuits, not only against IBM, but also against Microsoft, Amazon, and Google, who had downloaded this data set. And so this really showed that this is an area where even if you have pretty positive intentions in terms of wanting to address issues like fairness, if you are using data that has been inappropriately sourced, this can create significant legal liability. And so in terms of the reasons why we see these tensions in computer vision, it's worth considering what we're trying to do from a fairness perspective in particular. So since the seminal Gender Shades paper, there's been a lot of recognition in the field that underrepresentation in image datasets is a significant source of bias in downstream models. So if you have datasets that are highly skewed towards one demographic group, it's no surprise then when later on such models do not necessarily perform well on other demographic groups. So that creates a lot of motivation for diversity in these groups, but a lot of open questions in terms of how you actually obtain that diversity. In addition, we're not just interested in diversity along demographic attributes, but diversity in terms of subject-object interactions, subject-subject interactions, the backgrounds, the representation, so on and so forth. So the revised paper, for example, showed that there's a lot of issues in terms of how classifiers work with these sorts of representations. So you can see at the top level, the confident, correct female classifications are women depicted in these sorts of portraits, very dreamy, very pretty with like flowers around them. And if we look at the bottom row, the confident, correct male classifications, these are men in more formal occasions, more like flowers and sort of a head of state situation. And so that shows a very significant difference in terms of how women and men are depicted in conjunction with flowers in these sorts of data sets. And so if we want to avoid these spurious correlations, we need not only balance in terms of demographics, but more balance in terms of all of these other interactions as well. And then finally, in terms of any sort of bias detection or mitigation techniques, by and large, they do rely to some extent on the presence of sensitive attributes. And so if you don't have, for example, access to a label for gender, it's quite difficult to do anything in terms of testing for gender bias. So this also creates additional privacy concerns because sensitive attributes are sensitive from a legal perspective as well, meaning that if you want to collect this data, there's a much higher burden in terms of the consent and also how you process this information. So in light of these tensions, we see that there's a lot of challenges in terms of sourcing ethical human-centric computer vision data as a result. So most of the existing data sets that folks have available to use and most of the ones that are cited in conferences, including at CVPR, are collected via web scraping and do not have any form of informed consent of the individuals. They're by and large from Flickr, Google Images, other sorts of sources where it was impossible for the image subjects to actually know of these downstream uses and consent to them. In addition to that, when folks have tried to collect image data sets with consent or tried to use synthetic humans, we've run into issues of lack of diversity and realism. And so typically, if you're using folks that have fully consented, there's the issue of things looking very staged and coming across as images of actors, in that you have very clear specifications for how they should appear in the images, and it's far less natural. And then when it comes to synthetic images, there's still a domain gap in terms of how these images appear compared to real humans. And so in terms of why it's so difficult to actually address this and move beyond this, there's several challenges when it comes to collecting data sets more ethically. So one is that it is very expensive to properly source data. So a lot of images, if you are trying to do them, collect them with informed consent, would cost at least several dollars per image, which if we're talking about billions of images can be quite cost prohibitive. In addition, it's quite difficult to define and practice what are appropriate diversity specifications. Even something as simple as how many categories should there be for gender or for skin tone are extremely difficult to define and then have balance around. And any sort of definition is going to be prone to problems that will then get amplified in the data set. There's also challenges in terms of representation and exploitation of underrepresented communities. So it's easy to say something like, oh, if we find that your model doesn't work well for Indigenous people, why don't you go out and collect more images of Indigenous people? But that is quite non-trivial in practice in terms of how do you do that in a way that is non-exploitative. And indeed, there have been problematic stories in the past, for example, where companies have tried in the interest of fairness to achieve more diversity, but have run into additional ethical problems. So Google, for example, a few years back was in hot water when there were all these headlines that said that Google was preying upon homeless people in order to collect more diverse data sets. And that's because one of the vendors they were using were targeting homeless individuals in order to try to increase the diversity of the images they were collecting. So that's a huge problem and is something that has not been systematically solved completely. In addition, there's a lot of challenges when it comes to scaling across various countries' laws and regulations. So usually with any data sets that have been collected with informed consent, they're only going to reflect a few jurisdictions because every jurisdiction you go into, you need to comply with their idiosyncratic information privacy laws, IP laws, and other related laws. And even though we would like ideally to have globally diverse data sets, it's extremely difficult and onerous in practice to achieve this. And then finally, not only do you need to obtain informed consent under appropriate laws, but many privacy laws also have terms around consent revocation that can create many challenges as well. So that what that means is not only do you need to ensure that people freely give their consent, but then at any point they can revoke their consent. And of course, if you are paying people for their data and then at any point they can remove themselves from their data set, this creates potential loopholes and also challenges for downstream developers who are working with data sets that are constantly in flux. So in light of all of these challenges, it's worth considering what exactly are the harms that we're trying to address, and then is there any way that we can thread the needle in terms of simultaneously addressing privacy and fairness related harms? So first off, on the privacy side, there's not a lot of case law on this right now because by and large, most of the cases have been settled out of court. But if we look at the information we do have available thus far, three of the major concerns that the judiciary has expressed and also legislatures have expressed around the use of people's biometric information for developing HCCV include, for one, concerns around identity theft. So basically the worry here is the moment you go from an image to extracting people's biometric information in the form of facial geometries or face templates, that this would somehow enable other people to steal their identities. Of course, it's worth considering here, and we'll get to this as well in the possible solution section, but is there a distinct harm to using public images for training or evaluating HCCV systems, or is the harm at the point of these images becoming public? So that's kind of a question there. In addition, and this is probably the factor that is most motivating a lot of the regulatory developments in the space, there's a lot of concerns around mass surveillance being facilitated by HCCV. And this is also part of why at the beginning I really stressed that we're not only talking about facial recognition systems here, we are also talking about things that are arguably not for mass surveillance. But when it comes to any sort of cases around this, the specter of mass surveillance always comes around as something that is a huge concern. And here it's worth considering whether the use of identifiable images in reference sets is like the main issue that we're concerned with versus whether it's the use of more anonymous images in the training or evaluation process. And then finally, and this is one that is perhaps the most difficult to solve and the one that privacy law very specifically is oriented towards at the moment, is giving people a sense of control over their information. So if we see a lot of the news reporting around a lot of these cases, a lot of the concern has been around just how creepy it is to realize that your face or your child's face was used in developing a technology that you might or might not support. So that's a lot of the motivation that people have from a privacy perspective. Now, moving from privacy to fairness, what are the harms precisely that we want to prevent here? And I call these the harms of being misseen and privacy, the harms of being seen. So there's a variety of potential harms here. I've broken this down into 4 categories. So first we have allocative harms. So these are when HCCV inaccuracies or misrecognition can lead to the misallocation of goods or opportunities. And some of the highest stakes examples here are around the wrongful arrests of individuals. And in particular, in the US, we've had several cases, and every year there are more cases in this vein of Black males who have been wrongfully arrested, who have been detained, spent time in jail, or paid significant fines due to misrecognition of facial recognition technologies by law enforcement. And so this is a significant harm that we're trying to prevent here. In addition, there are representational harms. So this is when HCCV systems represent certain groups in negative, offensive, or otherwise problematic lights. And a famous example of this was back in 2015 when it went viral that Google Photos was improperly labeling an image of 2 Black individuals as gorillas. And this is a problem that to date has really not been fully systematically solved. A recent New York Times article found that Google Images and similar services are basically addressing this issue by preventing identification of gorillas, baboons, chimpanzees, orangutans, monkeys, related creatures. So this is a very important and very significant harm, but there's not necessarily complete solutions yet for this. In addition, there are concerns around differences in service provision. So this is if you are using a service or a product that has HCCV in it, but you have a fundamentally different experience due to your protected attributes. An example of this is there was controversy around some automatic blink detectors in cameras that kept asking Asian individuals incorrectly if they were blinking. And this was especially pernicious given a lot of harmful stereotypes around Asian eyes. And so, this is another type of harm that we want to prevent from a fairness perspective. And then finally, we have security threats. And so this is when specifically worse performance of HCCV can lead to unauthorized access to people's devices, bank accounts, so on and so forth. And a famous example of this was back when the iPhone X was released, and there were a lot of complaints in China that people were finding that their friends or family members were able to unlock their phones. And specifically, there was a case that got a lot of publicity where a woman found that her son was able to unlock her iPhone. So similarly here, lack of appropriate accuracy rates for certain subgroups can create significant harms. So now that we've gone over the relevant harms for privacy and fairness that we want to prevent, the question is, how do we thread these together and actually prevent these in practice? So I've put these potential solutions into 3 buckets. I will caveat this by saying that the nature of this tension is that none of these solutions are perfect. I wouldn't say any of these are silver bullets. All of them have pros and cons. If you want to know in greater detail, definitely check out the paper. But this can at least give us a sense of possible directions. So first off, and perhaps most controversially, is creating carve-outs from privacy law. And I say controversially because we're at a time where, if anything, people want more privacy perspectives rather than less. So this is not necessarily something I'm avidly advocating for, but just putting on the table. So one possibility here would be to distinguish between images that are used to develop HCCV models, so meaning being used in the training or evaluation process versus images that are actually used in deployment, meaning either being ingested by the model or used in some sort of reference set. And the motivation here is that if our primary concerns are mass surveillance and identity theft and harms like that, then arguably those harms are most problematic at the point of deployment in terms of the images that are processed at that point, rather than during the development process. So to the extent there can be a distinction there, we can maybe have our cake and eat it too in terms of using a lot of images for development, but and thus addressing some of the concerns about fairness, but not using them in this deployment context. Other possibilities in this vein include making biometric privacy laws more domain-specific or sectoral. This is motivated by the fact that one unique feature of biometric information privacy laws is they apply just to a type of information rather than to domains. So it doesn't really matter if we're talking about putting TikTok filters on, or if we're talking about facial recognition for law enforcement. All that matters is that biometric information is being processed. And so if these laws were more domain specific, that might help address some of this asymmetry where anti-discrimination laws and contracts are very domain specific. Another possibility would be to make identifiability a salient factor when evaluating biometric data collection or processing. And again, here, the idea is that if the primary concerns are around issues like mass surveillance and identity theft, at some point in the line, an identification needs to be made in order for those harms to happen. And so by making that a salient factor, we might be able to distinguish between high or low risk use cases. And then finally, a possibility would be to create carve-outs for bias detection and mitigation. And this is especially relevant in the context of sensitive attributes, which right now are extremely difficult to collect under privacy laws, but are very important for fairness. And this is something that the UK has actually done, so it's not unprecedented. Another possibility, so the previous ones primarily addressed the issues of mass surveillance and identity theft, but didn't address the issue of people feeling a lack of control over their data. So another possible set of solutions is around alleviating people's concerns around being seen or having their data being used for the development of HCCV. Options here include participatory design. So this has been something proposed in the literature in terms of trying to engage stakeholders more directly who might be users or might be affected by the technology. And I think this is quite promising for small scale bespoke data collection where that might be serving a certain community, but it does have some challenges in terms of how do we do this on a global scale? How do we think about this for large foundation models that ingest huge amounts of data? So it's not necessarily a silver bullet, but definitely promising. Another possibility is trusted third-party data collection. So this is also something that has been explored in the literature. And this is the idea here is if people don't trust large companies collecting their data, why don't we find a trusted third party that might be a better nexus for that? And the challenges here are identifying what that trusted third party is. So typically people point to governments, but there is a lot of negative precedents in terms of governments using questionable practices as well in terms of data collection for these purposes. Like NIST's facial recognition vendor tests did make extensive use of mugshots, for example, so there was not really appropriate consent there. And then finally, in this category, there's the possibility of technological advances. So in particular, synthetic data generation, so you don't actually need real humans, or federated learning such that learning can happen without the sharing of data. So these are certainly promising directions that are maybe not quite there yet in terms of being able to solve this problem completely, but definitely something hopeful for the future. And then finally, the other possibility here is that one challenge we have at the moment in practice for folks who are trying to implement responsible AI solutions is that you have a lot of regulations on the privacy side that are pushing towards a prioritization of that, but there's not really actually that much preventing the harms of being misseen or fairness harms. And right now, that's really just up to individual developers who care about these issues and want to make their products and services work well for everyone. So one possibility to balance things out a bit is to actually have a right against being misseen. So this could mean basically a right for HCCV systems to have some sort of minimum performance level for all people. There's a lot of problems in terms of implementing that, given some of the challenges around lack of industry standards in this space. So another option would be to establish an anti-discrimination right that basically would help protect individuals in the event of disproportionate performance or lack of performance for a particular subgroup. And this could be something that's enforced by an agency or private right of action. So those are just some of the possibilities in terms of how we might address these tensions between privacy and fairness in practice. In terms of overall takeaways, I would just emphasize that one of the major challenges that developers experience on the ground when it comes to issues like ethical AI is not just that we have a long list of things we want. So we want privacy, we want fairness, we want interpretability, trustworthiness, so on and so forth, but that a lot of these things in practice often are actually in tension with each other. And so if we want to make progress in this space, it's not enough to just say, okay, we're going to run in all of these directions simultaneously, but we have to really look at the intersection and think of how do we simultaneously achieve all of the goals we want and mitigate all the harms we want, especially in contexts where there might be trade-offs. And so with that, thank you all so much for your attention, and I'm happy to address any questions.
Time to take about 1 or 2 questions. So if you're in person, if you could go to the mic. If you're on Zoom, if you could type in the chat.
I have a quick question. You gave us a couple different options about mitigation. Is there one that you think is more promising than others, or do you think one is going to be, this is the one that seems like it's the best bet versus the other ones?
Yeah, that's a great question. So I would say I hope that this talk is more of an invitation to folks to explore these different options rather than kind of pushing for one of them over another. I think all of these are kind of early stage in terms of their potential and have a lot of problems with them in addition to the potential solutions. But I think one thing that would be really helpful is more awareness of this tension among practitioners and folks kind of more directly trying to tackle the intersection of the two.
So it's a wonderful talk. I'm really glad to see Sony and big companies taking this issue very seriously. We do some work on these issues in ethical AI in my research group, where we work largely on federal government funding, which adds another wrinkle on top of this. But setting that aside for a moment, you mentioned carbon as a potential solution to some of this. And I'm wondering how realistic you think that is. There's a number of examples where researchers have simply not worked on problems in any significant numbers because it was just too risky, because the carve-outs weren't there, or people's research efforts were trashed. And these were good problems that people wanted to solve: sex trafficking, child pornography, because you can't have these images. It's so difficult to have them. The legal protections weren't there. So do you see a possibility in a framework where, as these regulations come along, there could still realistically be carve-outs that would actually enable researchers to function such that people just wouldn't run away from the problem?
Yeah, that's a great question. And honestly, that's part of the motivation for this paper, because I mean, it's kind of ridiculous that it's almost impossible for someone to be a computer vision fairness researcher and work on human-centric computer vision without violating privacy laws. So, that's kind of very unfortunate if we're being very, very careful and very literal, of course. And I think that's true of a lot of different areas like this, where there's a lot of kind of unintended consequences to the legislation. And my concern personally with this is, I think a good scenario, as we're seeing more AI regulation come down, is that there would be a reckoning of these challenges, so that, you know, when people are looking at the additional, so for example, with the EU AI Act, there's a lot of language around your data sets need to be representative, your model and data sets need to be as free of errors as possible. You know, what does that really mean? But, you know, that in theory pushes us to care more about some of these issues of being misseen that I talked about today. If this is kind of an invitation to consider that and also think about existing laws like GDPR and how those intersect and interact, then I think that would be really beneficial, because then we could kind of protect both areas and have clear guidance in terms of these trade-offs. My personal worry would be, to the extent these laws just kind of layer on top of each other without any guidance, then at that point, it's really up to individual developers or individual companies to figure things out on them by themselves. And if we look at the history in this area, there's not been much evidence of really great practices that, you know, we want to just like kind of like scale up and such. And so there still needs to be work to figure out what actually would be a good practice, and hopefully more regulatory guidance around that.
Great. Let's thank our last speaker.
Thank you.
Thanks.
All right, so we're at the end of the workshop. Thank you for staying here until the very last minute. I don't really have a grand closing remark other than sharing this feedback form where we would, you know, just like to hear what things worked for us, for you, and what didn't. And also, if you're interested in organizing or reviewing for a future workshop or have speaker suggestions, we'd love to hear ideas. So please go to this link or use the QR code to fill out your responses. And yeah, I mean, the organizers, we're going to stay here for a couple of minutes, so feel free to come up to us, ask any questions. But thank you so much for, you know, being here and enjoying the workshop.
Oh, yeah, just but it's actually good. Worked out the video also. Thanks.
Yeah. Also,
Oh, yeah.
I've been trying to see him at like CVPR and probably like last year, but we never.
Yeah. This is the first one I've been to in person since COVID, actually. So yeah, it's nice to come back. And actually, I forget. So you're a PhD student. And you're in you finished your second?
Yeah.
Third year. Oh, okay. Wow. I'm twice.
Yeah.
So that was my first year. So how's it going? And you have a dissertation topic at this point, or
Explainable AI.
in general, or
In general, actually,
you're working with older, right?
I'm working with also after the this paper, and yeah, it's like that's where I'm paper. Well, they're still like interested in when it gets is wanted, like
Yeah, we're on
but yeah, I've been doing some work.
Yeah, no, I think
some are like more grounded, like some are purely part, and I'm trying to figure out how to like use this.
Yeah, that's a challenge.
Yeah, but I like it. And we did train how using the vectors which is
not Vera's, Arvin, I think I see for Canada.
Yeah. And I feel like there's a lot of it would be just it would have been the same results basically. Yeah, but like
Yeah, I actually love people doing that. But it does raise challenges, not only for like a, an individual piece of work, but, career-wise sort of challenges too. That people need to be willing to do it. So, and we need to find ways to make the incentive line up to the career-wise thing isn't a problem. But I don't shy away from it, just figure out ways to navigate it. I hope Pushkar can maybe touch base with you from time to time about some of the same. It's the first time you've organized something like this? I'm sure. You'll see you next time you're in China.
All right, see you. To serve you anyway. I was bad. Yeah. So thanks again.
Thank you so much.
Yes.
The workshop was like so enjoyable.
Okay, I'm so glad to
I
hear.
used to ask you about your paper hopefully on Wednesday.
Oh yeah, great. I'll take pictures of you presenting. I also I forgot his first name. Is it Dora?
Dora, yeah.
Yeah,
She was at choosing it.
Okay,
If you were there, you would have met her.
I was not. I think Ruth was, but I remember seeing her talk at the Explainable AI community.
She gives a lot of talks,
Yeah, so I recognize the name. I also saw your work when we're doing it.
Yeah, I did this work in Switzerland. I did like an internship with that group. I'm doing my PhD in Ireland, but I went to Switzerland for an amount of time. So yeah, it's collaborative thing. Yeah, that's how I got into the concept-based interpretation space.
Yeah, Vikram does a lot of work on that.
Yeah.
So concept-based explanations. We're just chatting about that topic. But you work on that on it.
Yeah, and you were involved in the network work as well, right? Oh, okay, you built on top of it though, right?
Kind
of. Related space, yeah.
Yeah.
But it's a really, really interesting field. I'm so glad I kind of got on board with it.
Yeah, great.
So yeah, I'll see you in the rest of the.
Yes, I'll see you on Wednesday or some other time at the conference.
All right, hopefully I'll get to see your poster anyway.
Yeah, I hope so too. Bye.
Saturday night.
Sort of understand.
And then I get my flight. So okay, it was like everyone was on the airport. I finished